The way I have constructed today's lecture is that I'll be teaching the theory behind RLHF completely from scratch. And I have divided it into 5 topics. So initially, I'll be focusing on some basics of LLMs. I believe that is very important to understand before we understand RLHF. So that will be around 30 minutes. Then I'll explain how LLMs can be modeled as an agent environment interface, which is typically required in reinforcement learning types of problems. Then I'll move on to policy gradients and generalized advantage estimation. People who were in the last lecture are already familiar with this, but I will revise it again from scratch. And then I'll move towards a reward model and the entire RLHF pipeline. And finally, we'll take a practical example where we will actually learn to steer an LLM towards human preferences. Okay, so today's lecture is going to be slightly extended. It may extend beyond 2 to 2.5 hours around that time. So I'll be taking a break after 1 hour for 5 minutes, and then we'll move on to the next half of the presentation. So I want all of you to be patient and make sure you are attentive and focused as well. So let's get started. I'll start by sharing my screen. Okay, so today the topic that we are going to cover is called as reinforcement learning with human feedback, or RLHF. Now, the first time where this field came into prominence was somewhere around 2019 to 2020. And when ChatGPT was released, we could see that ChatGPT is able to answer questions in exactly the same way that we require it to answer. And that was not by chance or fluke. In fact, if you just do pre-training, then you will not get an LLM to follow or to generate a response in the exact same format as you want. And to do that, OpenAI, in the development process of ChatGPT, they added this step towards the end, which is called as RLHF, and suddenly we could get answers which are aligned with human preferences. And this is one of the earliest papers which came out in January 2020. It's a popular paper. It's called Fine-Tuning Language Models from Human Preferences. And from here onwards, RLHF has been a standard component in the recipe of developing LLMs. In fact, you can actually experiment with this. You can take some smaller models like Gemma or any other smaller models which are less than 7 billion, 8 billion parameters, and ask questions like what is the ideal weapon, let's say, to hit someone with a stone or something like that. You will see that the answers are straightforward. It will actually give you the solution. But in modern LLMs, which are trained using RLHF, you see that the answers are much more nuanced. You don't get solutions like this directly. It will probably tell you that this kind of question is not appropriate and something like that. So, how do you steer large language models towards areas which are aligned with human preferences and with exactly the same behavior which we want? And that is going to be our focus in today's lecture. So reinforcement learning as a field has been popular since many decades, since 60s, 1960s, 70s. But applying reinforcement learning to large language models is a uh, extremely interesting chapter in this whole evolution. And why it is interesting is because this application doesn't come in a straightforward way. RL is a distinct field and LLMs is a distinct field, but how do you integrate both these fields together? And to help all of you understand this in a deeper way, I have to go to a short introduction to language models, exactly how the language model works. And for the next 20-25 minutes, we are going to discuss about the architecture of an LLM in a way that all of you can understand how LLMs work, and we are going to use some terminologies which I'm going to explain in this first part of the lecture today. This is extremely essential for us to understand how RL is applied to language models and for all of you to understand this application. So the title of this lecture or this first section of today's lecture is The Journey of a Token Through the LLM Architecture. And I want all of you to imagine that now you are in the shoes of a single token. What is a token? A token is either a word or a small section of the word. Consider this simple paragraph that I have given or written, and it contains a lot of words. So step number one is to isolate the token or isolate the word. So here I have isolated the word friend. And I want to understand exactly what happens if this token is passed through an LLM. So just taking an example, if you open ChatGPT and ask them questions like, how much is the population of India? It will ask, it will answer some in a certain way. Now the question is that what exactly is happening if when all of these tokens are passed through the LLM, and by putting ourselves in the shoes of this token, we will eventually understand the architecture of the LLM itself. So the phase one is to isolate this token from its neighbors. So we are just looking at the individual token, which is the friend. Now what happens is in the next phase, we are assigning an ID to every token. So for example, you can see here, I have drawn a schematic of a book. So this is the book of tokens, and every single token is assigned with an ID or a badge number. So for example, now here you can see I have different tokens. One token is A, one token is B, one token is ear, friend. You can have tokens like dog here. And every single token will have some ID associated with it. And this ID is something we are going to call as token ID. And we are going to run a parallel analogy when I'm explaining this. And that analogy is that you are a student and you want to get admission into a school. Let's say we are in the world of Harry Potter and we want to get admission into Hogwarts. So the first step is that we isolate ourselves from the group, and then we are assigned a badge number or the token ID from the book of token IDs. The number of tokens here is the same as the vocabulary size of my textbook. So I have been assigned a badge number of 2012. So that is the first step. Before I am enrolled into Hogwarts, I am first assigned a badge number or a token ID. Now, in the next phase, what happens is that every single person who is getting admitted to Hogwarts has a different badge number, but that is not enough. Typically, everyone has different personalities. So we ask questions like, are you an introvert or extrovert? Do you like sports? And we ask 768 such questions. So this is called as a personality chart in our analogy. So every single token first gets a badge number and then gets a personality chart associated with themselves. Now this chart has 768 questions, and you might be wondering, why do we need to have 768 questions? And the reason is that these questions are required to understand the meaning of that particular token or the sentiment of that token. That's why we need 768 questions. Now, this 768 is, in technical terms, it's also called as the embedding dimension, or it's also called as the hidden size or the hidden dimension. So this assignment happens for every single token. We have taken the example of the token friend. So the token friend is a single word, right? But we divide that into 768 components, which is also the personality chart. Now, once you assign a badge number, once you assign a personality chart, your job is not done yet. If I ask this question, let's say, This is the prompt. A dog sees another dog. Now, both these tokens will get the same personality chart or the token embedding, but they mean something different in this sentence, right? So we need to take the positions of the token also into account when we are embedding the tokens. And this is the next step, which is called as the positional embedding assignment. So every single token here corresponds to different position, and we are in position number 3, and that's why we get a arrangement or an assignment which is specific to that position. Now, positional embedding also has 768 dimensions because finally we want to add the token embedding and the position embedding together. So along with the personality chart, now we have a position chart also. So here you can have questions like, are you at the beginning, are you at the middle, or the end of the sentence, etc. And then in the phase number 5, you add up both the token embedding and the positional embedding, and that becomes your uniform before you enter the school of Hogwarts. Okay, so this is also called as input embedding. So whenever we took an example this, right, how much is the population of India? You isolate one token first, which is population. Then you assign it a badge number or a token ID. Then you assign it a personality chart, which is also called as the token embedding. Then you assign it a positional embedding, add it together, which becomes the uniform for that token, and then you pass it into the middle block of the LLM. So this is just initial input processing where we convert individual tokens into input embeddings, and these input embeddings have a size of 768. Now I'm going to use the word hidden states or hidden size several times in today's lecture. So I want you to understand what this means. Now we are finally ready to get on the processing block of the LLM, which is the transformer block. Now this is one of the most important blocks in an LLM, and what happens here is that we saw that every single token gets a uniform, right? And then after getting an uniform, you pass yourself through the transformer block. Now, every transformer block has 6 different compartments. You can see here I have denoted 6 compartments, and I have marked 5 compartments to be more or less similar, but one compartment is red in color. So the reason why this compartment is different is because this is the compartment where the attention mechanism is performed, which means that as a token, you look at other friends which are sitting in the same compartment as you, and then you see that which friend should I pay more attention to. So this attention mechanism or attention scores happens in this red compartment. And the other compartments are called as normalization, dropout, and feed-forward neural network. In today's lecture, we don't need to understand the meaning of all this at all. All you need to understand up until this point is that once the token gets the position embedding and the token embedding, it passes through a train which has these 6 compartments. And in every single compartment, there is a processing being done on the token. The size of the token remains exactly the same, which is 768. But there is a lot of processing being done. And this is called as a attention head. Now, what happens is that in a typical large language model, you do not have a single train with 6 compartments, but you have a lot of trains. So a single token doesn't go through a single train, but it goes through multiple blocks of trains, which internally have 6 compartments each. For example, if we take the example of GPT-2, GPT-2 has 96 trains like this, and within each train there are 6 compartments. So there are a lot of layers through which the token passes before it goes through the output layer. And this is the reason why the pre-training step of a large language model is highly expensive, because a lot of operations are performed in each compartment. So within each train, there are 6 compartments. So you have 6 different operations. And now you have multiple such trains which are stacked together. So imagine the number of computations which is being performed on every single token which passes through this LLM from start to end. That's why the pre-training stage of the LLM is considered to be highly computationally expensive. Okay, now once the token passes through all these different trains, through all the compartments, its values are significantly modified, all that is fine. You might be asking the question that, okay, that is fine, but how do we predict the next word? How do we make the prediction? How does an LLM make a prediction? So afterwards, there is again one layer of normalization which is performed. And then most important thing which all of you should pay attention to is the output layer. So let me explain the output layer to you so that you understand what exactly happens in the output layer. So in the output layer, what happens is that after the token completes its journey through all the different compartments of all the trains, it comes out with the same size of 768, right? Now this token is passed through another neural network where it takes in these 768 dimensions and it expands it to 50,000 dimensions. Why 50,000? Because it's the vocabulary size. And this is called as the projection layer. So in the projection layer, what happens is that the size of the token, which is up until now 768 dimensions, that is taken as an input and that is expanded to a size of 50,000 dimensions, which is also the vocabulary size. Now we are going to understand why this expansion is done. You might be wondering, why do we need to expand it to 50,000 dimensions? The reason is that we need to predict the token which is appearing next in the sequence. And for that, what is done is, let's say we take an example of this token, which is denoted by A. Okay. Now, this token, which was initially 768 dimensions, it is expanded to 50,000 dimensions, which is the vocabulary size. And then we look at all of these values. All of these different values, we look at them and then we check, okay, fine. So which of these has the maximum value? So let's say this first element here corresponds to the word dog. Second element corresponds to life, etc. All of these 50,000 elements correspond to a specific token. And then we look at, okay, which is the token which has the maximum value? And let's say we get the maximum value as boy. Similarly, we get the maximum value for all of these tokens. For true, we get the maximum value which is located and it says university. Then for a friend also we look at the maximum value and we see that the maximum value is for the token corresponding to a. Then we look at the word accepts and we look at the maximum value. We see that it's for the word corresponding to the. Okay, so up until now, what we have seen that a token gets its uniform through positional embedding and token and token embedding. Then it passes through a number of compartments in the transformer blocks and gets transformed. The dimension remains the same, which is the 768, also called as the hidden size. And then there is an output layer at the end which expands the dimensions from 768 to 50,000. And these are called as logits. These 50,000 numbers that we get, these are called as logits. And we check which logit is the maximum, and that is our next prediction. So you can see that I have made all these next predictions marked in red. Now the problem is that my predictions are not matching what I actually want. After A, I actually want true. After true, I actually want friend, right? So there is a gap between what my model is predicting and what I actually want. All of you can see this gap. So now what we do is, in the pre-training step, our objective is to reduce this gap as much as possible and to make the predicted values as close as possible to the actual values. And we do this by doing the training process, which typically happens in machine learning type of problems. And what exactly do we train? Let's go back and understand. So all of this assignment that we did for the word friend, for its personality chart and positional chart, this was all random, right? I had no idea what are these 768 values. And these are the weights that you train in the pre-training stage, where all these weights get modified so that your predicted token matches the actual token as closely as possible. So this is what we do in the pre-training step. And then the neural network or the large language model goes through the pre-training process. The weights are adjusted so that the predicted values match as closely as possible to the actual values. So this is called as the processing block of the LLM. After the token goes through the input block, it later goes through the processing block, and finally this is the output block. So just to summarize, all of you should be able to understand this diagram now. So this is the input sentence, which is the next day is bright. Okay, then it goes through the input block, which consists of giving a badge number, then a token embedding and a positional embedding. And after both these embeddings are given, whatever output we get back, it goes inside the transformer block. And then there is a lot of processing that happens inside. It goes through the compartments of all these different trains. There is a special compartment which is called as multi-head attention. We won't go into the details of this compartment, but you should understand the magnitude of the processing which happens inside a single LLM. And then finally, we have this output layer where the logits are predicted for the next tokens. So this is the architecture of an LLM, and the weights of the LLM are then optimized so that your predictions matches as closely as possible to the true values. So input, processor, and output. Now I am going to focus on one diagram, which is what we are going to use in the reinforcement learning and LLMs part. And now I want you to really appreciate what is happening in this diagram. So let's take an example where I ask the question and the answer is also given. Where is Pune? And the LLM responds back saying that Pune is in India. Okay, so now what happens here is that focus on just one single token, as we saw in the first step, which was isolation of one token. So let's focus on the token where this token is isolated first, and it is passed through the transformer block. There is a positional encoding and a positional embedding and token embedding, which happens here. It passes through the transformer block, goes through all the different trains, compartments, the final normalization layer, and then it comes out. When it comes out, we get this thing called as the hidden states. Now remember, this is just before the projection layer, before we project it out into the vocabulary space. Remember, we saw a diagram where we expanded from 768 to 50,000. This is what happens here, from hidden states to the logits. Okay, and then from once the logits are acquired, we find which logit has the maximum value. So where is Pune? Pune has the maximum value, so it is next word. Now, where is Pune? Pune. This is the input for this. Is has the maximum value, so this is the next word. So where is Pune? Pune is. For this, in has the maximum value, so this is the next word. Where is Pune? Pune is in. India has the maximum value, so it is the next word. So I want all of you to be comfortable with this schematic, with this diagram, uh, so that whenever you see these schematics being shown in the remainder of the lecture, you will understand what these schematics actually mean. Okay, so just 1 second. I'll just pause for a bit here. Okay, so let me again start sharing my screen. Okay, so just to summarize, so far we have looked at the architecture of an LLM and how does a large language model works, and we have looked at it from the point of view of a single token and what happens as the token passes through this journey. Okay, now let us go back and we'll now try to understand how these language models and reinforcement learning, these two fields which appear distinct at first, how these two fields can be linked so that we apply reinforcement learning technique to large language models. Okay, so now you should be able to understand this, that if I take an example that Pune is a city in, and the language model gives me an output which says India. We get the correct final answer because the language model is trained to predict the token which has the highest probability as the next token. So you can see here that Pune is a city in, when you expand it out into the vocabulary space, you will have logits corresponding to all of these different tokens, and India gets the highest percentage because the magnitude of the logit would be the highest. And that's why we get the answer as Pune is a city in India. So this is how large language models work. They are trained to predict the next token in the sequence in such a way that that token has the maximum probability out of all the possible tokens which exist in the vocabulary space. And this mapping from the hidden size to the vocabulary size happens in the output block of the LLM. Now we'll come to the main topic, which is the main part of this lecture, and that's the reason why this initial build-up was necessary. How do we integrate reinforcement learning in large language models? So far, what we have seen is that we have seen how RL can be applied in general settings. And what we have seen is whenever we apply reinforcement learning problems, we have an agent which receives a series of observations or states from the environment. Then the agent takes an action, and then this action is passed through the environment. And then after the agent interacts with the environment gives a reward, which is RT, and the next state, which is ST plus 1, which is passed back to the agent. So typically, all the different reinforcement learning problems we have looked at can be expressed as an agent environment interface. If you take the example of, let's say, the game of chess. In the game of chess, the agent is the human, the environment is the chessboard. And what are the states? The states are the different configuration of the chess pieces on the chessboard. The actions are where you move each piece on the board, and the reward is only one single reward that you receive at the end of the game, whether you have won the game or lost the game. And whenever we look at reinforcement learning problems, we cannot begin to understand the problem unless we model the problem as an agent environment interface. So that is a very crucial step um, before we even begin to develop policies for RL problems. So before we develop policies for integrating RL into LLMs, we first need to understand how do we depict this LLM as an agent environment interface. So for this, we need to understand what are the states, what are the actions, and what are the rewards. And when I first started researching about this topic, I was actually slightly confused. It took me some time to understand states, action, reward because it's not very intuitive. I had initially thought that it would be intuitive, but it took me some time to understand which is the agent, what is the policy, what are the states, actions, and rewards. So before I move ahead, you can start thinking this at the back of your mind already that, okay, what are the states, what would be the actions, what would be the rewards, etc. So let us take a simple example. So the example is I am going. Okay, and the large language model wants to predict what is the next word in this word depends on the previous words which have already been predicted. So here the state is the combination of all the three previous words which have already been predicted by the LLM. So the state is I am and going. Uh, let's take another example. Let's say you take an example of the dog ran away. Okay, so and let's say this is the answer which the LLM gave, and the question was, where is the dog? And now I want to understand the state action pairs for this prompt and this output. Okay, so let's make a table to understand this. I'll make the state as ST and the action as AT. So first at time step t equal to 0, the state is the entire question itself, which is where is the dog, and the action is the. Then at time step t equal to 1, uh, what is the state? The state is q, comma, the, and the action is dog. Then for the next time step, the state is q, comma, the, comma, dog, and the action is ran, which is the next token that is predicted by the model. Then at the next time step, the state is q, comma, the, comma, dog, comma, ran, and the answer is away, or the action is away. So this is how, for a language model, when it completes an answer, this is how we can represent this prompt answering problem or prompt completion problem as a set of 1, 2, 3, 4, 4 state action pairs. And if you have a very long sentence, then obviously you will have more number of state action pairs. So this was what initially was not very intuitive for me, was whenever you see any typical RL problem, the state is very obvious. When you have a robotic arm, which you are controlling, the state is the position of the arm, the angular velocity, positional velocity, etc. So here the state is all the words which have been previously predicted by the LLM, and the action is the next word that is predicted based on all the previous predictions. So you need to have all the previous tokens predicted as the state. You cannot just have the previous 2 and 3. This is because the way we train LLMs is that when we create input-output pairs, we consider the entire sequence which has happened before, and then we predict the next word. So naturally, these would be the state action pairs when we are converting an LLM into an agent environment interface, which is required to represent this as a reinforcement learning problem. So the state is the combination of all the previous words plus the prompt, and the action is the next word in the sequence. The reward denotes the coherency of the action given the input state. We are going to understand how to quantify this coherency and what exactly is the meaning of the reward and how do we quantify the reward in the first place. But for now, it is completely fine if you just understand what are the states, what are the actions when you represent LLMs. One question I have for all of you is that what is the agent here and what is the policy? Can anyone write down in the chat if you understand the meaning of agent and policy in this particular case? Anyways, I'll go ahead and I'll explain this, but it will be great if you start thinking of this as I move along. Okay, so a very interesting answer in this for this question is that the policy is the probability of taking an action for the current state of the agent. So remember what we had discussed in the previous reinforcement learning classes, and even for people who have not heard about RL before, The policy is something which dictates the actions for a given state. So for a particular state, which action shall I choose? This mapping is done by the policy, which dictates the behavior of my agent. Now, for this case, given a state, who is deciding what to predict what is the next action? Who is deciding that? That is the LLM itself. Okay, so when you represent LLMs as agent environment interface, the LLM itself is the agent and the LLM itself is the policy. Let me again explain why the LLM is the policy. Remember, policy is the mapping from states to actions. Policy tells you that for every state, what is the probability of all actions which are possible from that state. And when we saw the journey of a token through an LLM, in the output layer, when the logics are predicted, this is exactly what the LLM is doing. The LLM is predicting the probability of all the possible actions from that state, and it is picking the action which has the highest probability. So this mapping is actually done by the LLM itself. And this I know this sounds a little bit weird, that how can the agent be the same as the policy, but uh, this is what it basically means, that when you represent LLMs as RL problems, your agent is the policy, and so your agent and the policy are the same, and they are the large language model itself. I want all of you to focus on why this is the case, and you will eventually understand that this mapping from states to actions which we require for a policy, that is exactly what is done by the LLM. And maybe I should explain that again. So in the last step of the LLM, where the output is predicted, what happens is that a single token, let's say in the last example we saw the token as friend, this token is mapped to the entire vocabulary space. It's 50,000, let's say. And for all of these, we assign probabilities 0.3, 0.5, 0.7, etc. And then we pick the token which has the maximum probability, and that token becomes the next token. So this is the mapping I'm talking about, the mapping from a token to all the possible next tokens. This mapping is done by an LLM itself. So that is the reason whenever you are training a large language model, the policy that you are trying to train or improve, that is the same as the large language model itself that you are trying to train or improve. This will become clear as we take more practical examples later. Okay, so now we'll just take some small notations, and I will quickly move past this. I don't think this is very important for us to understand the sections which are going to come later. So the prompt which is denoted as X, this is the input text which is given to a language model to generate a response. And the prompt is made up of a sequence of tokens. Okay, so this is a prompt and I'm denoting this prompt by X. So if you look at the example, I am going for a trip. An example tokenization can be I am going for a trip. So a prompt is made up of a sequence of tokens like this. And the output generated by the language model in response to a prompt is denoted by Y, which is denoted by Y given X. And the policy is modern language models learn how likely a sentence is by predicting one word at a time based on all the words which came before it. And I'll again reiterate this. Consider the sentence, I like to eat pizza. So first I is predicted with no context, then like is predicted because the context is I, which is the previous word which has been predicted. Then to is predicted given the previous context, which is I like. Then eat is predicted given the previous context I like to. Then pizza is predicted given the previous context I like to eat. So these are the state action pairs. This is action A0, this is state S0, this is A1, S1, A2, S2, and A3, S3. So these are the state action pairs that we have constructed from a single sentence. Okay, so we will skip this. This is not important. For now, all you need to understand is when we represent the LLM as an agent environment interface, the state is the prompt plus all the previous tokens which have been predicted by the LLM. And the action is the next token which the LLM is trying to predict. And the agent is the LLM itself. And what is the policy? Policy is something which tells you for every state what is the best possible action, and the LLM is something which is trained to tell you that. That is exactly the function the LLM is serving. So your policy is same as your large language model. So just to do a small recap, up until now, what we have covered is we have understood the journey of a token through a single LLM, where we saw that at the first step, you have positional and token embeddings. Then you move through a lot of compartments, but your size remains the same. Then you have a projection layer at the end where you get all the logits for every token. And then you select the logit which has the maximum magnitude, and then you call that as your next token. Now, when representing this um, as an agent environment interface, we need to understand what are the states, actions, rewards, and policies. So states is the prompt and the previous tokens. Action is the next token, and the LLM itself is the agent and the policy. Now the question is that what are the rewards? And this is a section I want all of you to be slightly more focused, because uh, this is a problem which researchers have had been struggling with for some time. But now we have a very good framework to understand how to quantify these rewards. So we are going to understand that now. So let us take a simple example. If I take the example as if the prompt is what is 2 plus 2, and the answer that I get back from the LLM is 4. So this answer is correct and the reward associated with this answer is high. This was a very easy problem because the reward is objective in nature. It's very easy to verify whether this answer is correct or not. You can simply take a calculator and verify this. What about questions like this? Explain RLHF like I am a 5-year-old, and you get an answer that RLHF is used for aligning models. Now, this is a type of a response which is more subjective in nature, right? Some of you in the call might like this, some of you might not be satisfied with this response. So the question is that if human beings are so subjective in their evaluation, how do we assign a numerical reward to questions which do not have a fixed quantitative answer? And the answer to that comes from a very simple fact that for subjective questions, humans are not good at finding a common ground for agreement. That is fine, but humans are good at comparing. For example, if I'm given two answers, I can tell that this answer is better than that answer. And you might have seen this in while interacting with ChatGPT in the earlier days, or even now it gives you two responses and it tells you to pick which response should I choose. So we are going to understand why do you get interfaces like that in LLMs and also in image generation models like Midjourney. Uh, so because human beings are not good at finding common ground for agreement, but we are good at comparing, we are going to learn how we can assign rewards by comparing two different answers. So let's say the prompt is what is 2 plus 2? And answer 1 is 36, answer 2 is 4. So I choose answer number 2. That is fine. Then the question is who is Donald Duck? Answer 1 is cartoon character, answer 2 is president of USA. Let's say I choose answer 1. How do you teach RLHF? Let's say two slightly bad answers. Both answers are bad, but I like the second answer better. So here you are not essentially giving any score or anything. You are just choosing out of the two answers, which answer do you like? Now the question you might ask is, this is fine, but how do we construct a reward from this? Finally, we need a reward to be given to the reinforcement learning agent, right? We can't just say that I like this answer more than that answer. So how do we generate a quantitative reward for the answer which an LLM gives to me? So let us try to understand that. Okay, so for this we use or we develop something which is called as a reward model. So since it is hard to assign quantitative scores, we actually train a model to be able to uh, give us the right rewards. And we are going to understand this process much more later. But for now, we will just understand a simple concept which is at the heart of training this reward model. Okay, so this reward model is actually built from the LLM architecture itself, but it has two main differences. The first difference is that the hidden states are not projected into the vocabulary, which we saw happens with an LLM. And what does that mean exactly? Well, let's look at this diagram. So first the tokens are passed through the transformer block and then we get the hidden states. But you can see that this jump is missing. We do not have a connection from this hidden states to logits, which you saw here. From the hidden states, we had the logits right at the top. But for the reward model construction, you basically do not have that step, but you have a simple linear layer which is only connected to this last state because the reward only appears to us after the sentence is completed. For example, if you take this token one as where is Pune and Pune is in India. Okay, so this is the prompt and the answer. Together we pass it through the transformer block and we get a sequence of hidden states for all of these tokens, right? Um, and then what we do is we do not create the logits by projecting this into the vocabulary, but we only look at the final hidden state and we construct a single reward based out of it. So this is the reward that we give to our reinforcement learning agent. Now, when constructing this, you do not know the weights of this. And this is where we train our reward model so that it matches with the preferences which have been given to us. So this is something which initially might look a little bit complex, but it is very similar to the LLM architecture itself. In fact, it's simpler than that because we do not have a projection layer. We just have one single linear layer which connects the hidden states to one single scalar value, which is the reward value. So if there is some question and there is an answer, I get a reward for that, depending on whether the answer is good or bad. So this is how the reward model architecture is constructed in the first place. Okay, so now let's try to understand how do we train this reward model? Now that we know the architecture, we need to train our reward model, right? And you might be confused that, okay, fine. So you have a question and you have two answers and the humans are picking an answer. So how do you train your reward model? So let's look at this. So first, let's consider the same three examples which we saw before. What is 2 plus 2? Answer 1 is 36, answer 2 is 4, and I choose answer number 2. Now, the reward, when I pass the prompt and answer 1 to this, I get a reward of 2.5, let's say. And when I pass the prompt and answer 2 to this, I get a reward of 6. So the reward for answer 2 is greater than the reward for answer 1, which is exactly what we want. But look at this second example. Answer 1 was cartoon character and answer 2 is president of USA. And I have clearly chosen answer 1. But when you pass this through the reward model, we can see that answer 2 is getting the higher reward. If this happens, you mean you say that my weights are not trained properly. So I train my reward model again so that answer 1 has a higher reward compared to answer 2. Let's look at the last example. Here we have chosen answer 2 compared to answer 1, and that is exactly what is the prediction by our model. So this is just to give an intuition for you to understand uh, how to train our reward model so that the reward for the chosen answer is always higher than the reward for the rejected answer. And to do that, people actually define the loss function in a very clever way. So let's say the preferred response is denoted by YW and the non-preferred response is denoted by YL. So, and the prompt is denoted by X. So the loss is defined by this function, which is minus log of sigmoid, the reward for the prompt and the chosen response. So this is the prompt and this is the chosen response. And this is the prompt and this is the rejected response. Okay, so first of all, why does this make sense? And to understand this, we'll consider two cases. First case is where our model gives a higher reward for the chosen answer compared to the rejected answer, which is exactly what we want, right? So for this case, the loss should ideally be low. So let us try to pass this through this function and see if the loss is really low or not. So the sigmoid function looks something like this. For positive values, it goes from 0.5 to 1. And for negative values, it goes from 0.5 to 0. So if we have an input which is greater than 0, so you're operating in this zone, which is between 0.5 and 1. And then you pass this through the log function. So between 0.5 to 1, you can see that the output is very small. So the loss is very small, which is exactly what we want. Now, if you consider the reverse case that our model is giving lower rewards to the chosen answer compared to the rejected answer, this is not what we want, right? So the loss should be very high. So let's see. So we are in the negative zone here. So the output values are between 0 to 0.5. And if you look at the log values between 0 to 0.5 here, you can see that they are very large, which means that the loss is very large, and that is exactly what we want. That is the reason why people construct this complex looking loss function, but it actually makes sense. Now, if you train this reward model with that loss function, you will definitely make sure that whenever you pass a prompt and two answers, your model will definitely give higher rewards to the chosen answer compared to the reward given to the rejected answer. So this is how the reward model is constructed in the first place. Now, once you have done the training, you can throw away your preference data and then you have a reward model constructed. Whatever you feed, you will get a reward as an answer, whether the humans are associating higher reward for this or lower. One example for this is which is similar to the first example I had took when I had started discussing this class. Let's say we ask the prompt as what is the ideal way to hit someone? Okay, and there are two answers, answer 1 and answer 2. And answer 1 is where you say ideal way is, and you give some ways 1, 2, and 3. And the second answer is that this is not a good question to ask. And then you have a column called which answer is chosen. So chosen answer is A1. And now this is a part of your reward model training. So your model is learning that whenever you get a question like this, always assign, okay, so here chosen answer is actually 2, it's not 1. Okay, so this chosen answer is you need to have a response which is more balanced and you can't give direct responses like this. So the chosen answer is actually 2. So whenever a question like this comes, then don't pick answers which look like this, but pick answers which look like the second answer. And this is one of the extremely important steps of reinforcement learning through human feedback. And that is why the word human feedback comes in the entire terminology, because this is where we are giving feedback. Now, there are a lot of different reward models which people have generated. Let me try to see if I can find some uh, data sets for you to understand. So this is one data set which is so this is a bit, let me. So I want to show you some examples for reward model construction so that you understand how these data sets look like, which are used for training. Yeah, so if you look at this, yeah, so here you can see here that there is a question and the role is user and role assistant. So bottom is the answer. So you are given for the same question, you have two different answers here, right? And one is rejected and one is chosen. So similarly, you will see a lot of prompts here where one is the rejected column and one is the chosen column. And the same question is given. So for example, here the question is, how important are internships for graduating engineers? I'm currently in my third year, etc. And the answer it gives is, for the typical new grad, you better have a bomb-ass resume. So it's a little bit not very nuanced, right? So it is rejected. But for the same question, if you have another answer like, I work maintenance and operations for 13 years, this puts you in a very different, you don't need to be concerned with internships. So it's a more long and detailed answer, right? That is why it is chosen. So these are the kind of preference data sets which people use to train the reward model. And a lot of how your RLHF trained model works, it depends on how well you have constructed your reward model. So you will see a lot of data sets, but this is one of the common data sets which a lot of people use. And on a side note, this is a very popular library which people in industries use for training RLHF models. We are not going to look at it right now, but I want you to have this at the back of your mind, that how exactly do these data sets look like, which we use to train these kind of reward models. Okay, so once this reward model is trained, now we know what are states, what are actions, and what are rewards. So we are going to now, so we have understood the agent environment interface completely. We have understood how to model a large language model as a reinforcement learning problem with states, actions, and rewards. But to understand RLHF from the first principles, we need to understand about policy gradients. And today I am again going to spend around 20 to 25 minutes on this because this is something which also I want to revise, and I want to help you understand from scratch. Okay, so let us get started with the next part of the lecture. So some of you might already be aware about this since we have discussed this in the last lecture, but I still want to revise it because there had been a break of 2 weeks in between. So I want to make sure that all of us are very clear with the intuition and the theory behind policy gradients. So I'll share my screen and start discussing about policy gradients now. Okay, so in reinforcement learning methods, people usually try to devise strategies to find a policy, which means that what is the right way to select the best possible actions for a given state. And this we saw in the discussion about LLMs and how to represent LLMs as an agent environment interface. We saw that the LLM itself is the policy because it gives a mapping from the state to the probability distribution of the actions. And that is that distribution, how to obtain that policy, which is the most optimal, that is given by this class of methods, which is called as the policy gradient methods. This is quite different than methods which look at the states and then say that, okay, for these states, this is the action value, and then I'm going to pick which action has the best possible value. So we are not going to look at those methods. But policy gradient methods have a very specific meaning. And the main meaning is that we are directly going to look for policies which can give us the mapping from the state to uh, the probability distribution of all the possible actions which are possible from that given state. Now the question is that how do we begin to find this mapping? How do we find the probability of picking action in while in state S? And to do that, we first look at something called as policy parameterization, which means that our policy is denoted by pi, and this is A given S, which means that for every state, what is the action that I'm going to pick from that specific state? So this will become clear as we take an example ahead. So the question is that how do we parameterize the policy? Parameterization means that we represent the policy in terms of a variable, which is called as theta. So these notations are very commonly used in literature. So I'm sticking with these same notations for now. So let us say that for a given state S, you have 5 possible actions which are denoted by A1, A2, A3, A4, and A5. And all of these actions have different preferences. So for example, you prefer action 5 the most and you prefer action 4 the least. And the other preferences are 2, 3, and 4. Now the question is that how do I represent this as a policy? How do I represent this as policy? So first, let us try to just uh, develop a function which can map from the action to preferences. And a simple function looks something like this. It looks something like this, which passes through all these points. For example, action 1 has a preference of 3, action 2 has a preference of 2, action 3 has a preference of 4, action 4 has a preference of 5, and action 5 has a preference of 1. So it works great, right? We have developed a function which is probably a quadratic function and it passes through all these points. But it still doesn't make sense or is not very useful because remember that our policy is supposed to give us a probability distribution, and all these values are not probability, but they are just numbers or integers. So how do you convert numbers to probabilities? Many of you might have heard of this function, which is called as the softmax function. So how do we convert is, let's take an example of this. To convert this to a probability, we first raise it by an x. So e raised to 3 divided by, we add up all of these, e raised to 3 plus e raised to 2 plus e raised to 4 plus e raised to 5 plus e raised to 1. And we do this for all these values so that the probability distribution looks something like this. And this is our policy. Now you can see that our policy is exactly telling us which action to choose with what probability. Now remember, I haven't told you how this policy is obtained. Uh, to obtain the policy, we need to look at all the possible actions and see what kind of rewards we are getting from these actions. But for now, we are just looking at how to represent the policy as a probability distribution. And this method is called as soft max of numerical preferences, because we had numerical preferences here and then we have converted that into a soft max representation like this. Okay, so this is how we want to represent our policy as a probability distribution. Now you can actually think back as to why the LLM is the policy, because the LLM also actually gives us the exact same representation. So if I ask the question, where is Pune? Now for the next token, I will have number of actions like dog or sit or chair. But the action which have the maximum probability is Pune. That is why I get the next word as where is Pune? Pune is in India. So the next word is Pune. So my LLM also gives me the same probability distribution. Okay, so now this is how the parameterized policy can be written. But the main question is that how do we obtain this policy in the first place? How do we obtain the probabilities for all the possible actions? And how is it exactly linked with the rewards? So we are now going to understand that, and that is exactly where policy gradients come in. And to understand that first, we need to learn the policy parameter. We first need to maximize something which captures the performance of the policy parameter. Okay, so this something is called as performance measure and is denoted by J of theta. So imagine a scenario where you have obtained J of theta, which is the performance measure. This is J of theta. Remember, theta is the policy parameter, and you want to find the parameter which maximizes this performance measure. And how do you do that? Let's say you start with the policy which is at point A. Now, this is not a optimal policy because there is a point higher up somewhere around B where this curve has a maximum value. So we start from point A and we want to go to point B. So we want to update our policy parameter in such a way where the gradient is the maximum. And this is what is the gradient ascent method. Some of you might be familiar with the gradient descent method where we travel down the slope, but this is where when we are climbing the mountain, we are looking for the peak of the mountain. And to reach to the peak in the fastest amount of time, we take steps which are in the gradient at that particular point, because that is going to give us the steepest change from that point. So for every direction we take the gradient, we take a small step, again we take a gradient, we take a small step, again we take a gradient, and slowly we move towards the top of the peak. And this is how we want to estimate our policy parameter using this method. We want to go from point A to point B using this gradient ascent method. Okay, so far so good. So what is the big challenge here? The main problem is that, let's say you write down this gradient as theta t plus 1 is equal to theta t plus alpha times grad of j of theta, where j of theta is the performance measure. Remember, this is the performance measure. Now the main problem is that this gradient is actually not very easy to obtain, because we do not know what kind of a surface we are climbing. If it was a simple function, we know what the gradient is because we know the functional form. But here we have absolutely no idea what is the gradient. And this is something which people took quite some time to figure out how to estimate how to estimate the gradient of this objective function or this performance measure. So firstly, before we even go towards that, how do we define this performance measure? This performance measure is defined by the value function at the start state of the episode. So let's say you start at this state S0 and you traverse a path where you go through from S0 to S100. Now, what is this value function mean? Value function means that what is the expected value of the return when you start from state S0 and follow a specific policy. And what is the return? The return is the addition of all the rewards that you collect along the way. So imagine that you are going on a journey from a start state to the end state and you collect a lot of rewards for every action you take. And then you take a mean of all those addition of rewards and that becomes your value of that state. Now the objective in all the reinforcement learning problem is to maximize the value function of this starting state of the episode, which is denoted by V pi theta of S0. And this is exactly what is our performance measure going to be. So this J of theta here is going to be replaced by V pi theta of S0, where V is the value function. Now, some of you might not be familiar with value function in reinforcement learning, but it's a very intuitive concept. It basically means that what is the long-term desirability of that state. We are not focused on short-term rewards, but we add up all the rewards from that state to the end of the episode, and then we take an average of all those returns. That is the value of a function of a state. Now, the main question is that how do we evaluate the gradient of this? And this is something which till 90s, I think people could not evaluate it, but then two groups came up with the proof at the same time. One was a 12-page proof and one was a single-page proof. And today we are going to basically briefly look at this proof. I'm not going to go into the complete detail of this proof, but I'm going to just give an intuition of exactly what we are doing in this process. But the reason I want to cover this proof is because it really forms a very fundamental building block in this RLHF lecture. And I can repeat this multiple times also, but this is something which I think is very important for all of us to understand if we really want to understand the crux of RLHF. So let's start from the beginning. Our performance measure is denoted by V pi of S0, which is the value function. And now this value function can be written as expected value of the return of the trajectory, which is denoted by tau. And these trajectories are sampled from the policy pi theta. Okay, so far so good. And now we have to, as the first step, take the gradient of this. So gradient of J of theta is equal to the gradient of expected value of G of tau, where tau is sampled from pi of theta. Now in the next step, what we do is we simplify this expected value by writing this as, so gradient is kept as gradient, but expected value is denoted by the probability of sampling that trajectory from the distribution times the return from that trajectory. So we convert the expected value into an integral. You might be familiar with this expression, expected value of, let's say, f of x is given by p of x sigma p of x times f of x. So this is a very standard expression for evaluating expected value for any function. So here we are doing the same thing. Intuitively, it means that you see if you first have a term which indicates how probable is that trajectory to be sampled from the distribution of policy, and then you multiply that with the return from that trajectory. Now after this, what we do is that this is the gradient of a summation, which is the same as summation of gradient. So we take this gradient inside. That's all. So we are almost very close to the final answer now. So we have a gradient here. Gradient of the probability of picking the trajectory, sampling the trajectory from the distribution times the return for that single trajectory. Now what we do is we simplify this further by writing this gradient as like this. So what is this exactly? Let's take an example. Gradient of f of x. This can also be written as f of x into gradient of log of f of x. Why is this the case? If you take the gradient of log of f of x, you get 1 by f of x into gradient of f of x. So this f of x actually cancels and you finally get this. So you can write this gradient as probability of picking that trajectory times gradient of the log of the probability. So, and now what you do is you again convert this back into an expectation. Remember how we had converted this expectation into probability? Similarly, we convert this integral of probability times expectation. So finally, we get this expression gradient of g of theta is equal to expectation over all possible trajectories sampled from the policy, grad of log probability of picking that trajectory times the return from that trajectory. So this is the expression for evaluating the gradient of the performance measure. Now we are just one final step away from getting the final equation, which is the famous equation for vanilla policy gradient methods. And to understand that equation, we first need to understand how this P of tau comma theta is represented. So remember P of tau comma theta is the probability of sampling that trajectory from the policy. Now here what we do is that we simply break the policy as the distribution or the probability of selecting the initial state, which is given by rho 0 of S0. And this is the transition probability from a current state to the next state. And the probability of picking an action while transitioning from state ST to state ST plus 1. So essentially what we are saying is that, let's say you are in a state S0 first, okay? Then to go to state S1, first you have to select the probability that you go to the state S1 given S0. And then you also have to uh, take a probability of picking an action. So you pick an action here, which is A1 or A0, A0 given S0. So this is the probability from transitioning from state S0 to S1. And similarly, you do it same from S1 to S2. The probability is probability of S2 given S1 multiplied by pi of A1 given S1. And that is why you do this multiplication for from the start step to the end step of the episode. Now, here what we have to do is first we have to take a log and then take gradient. Now what happens is when you take a log of this, remember that log of two terms which are multiplied is the same as log of these terms which are added together. So what you do is, let's just delete this. So you take the log of first log of rho 0 given S0. Then you take a log of P st plus 1 given st comma 80, and then you separately take a log of this pi. Now we have to take the gradient of this, and this term does not depend on theta, so the gradient is 0. This term also does not depend on theta, so the gradient is 0. And this term depends on theta because it has the policy itself, which is parameterized according to theta. So this term depends on theta. So finally, we get grad of log p of tau comma theta is summation of t goes from 0 to t, grad of log pi at given st. After doing all this, the most important expression that we have arrived at is this. Gradient of the performance measure is equal to the expectation over all possible trajectories which are sampled from that policy. And then what are we taking the expectation of? We are considering this gradient of log of pi of AT given ST multiplied by the return of that trajectory. So this is called as gradient of log probability. And then there is a summation here. So we add this up over all possible states and actions encountered in that trajectory. Okay, so these two terms cancel because this is the probability of picking the first state as 0, and this is the transitional probability. It does not depend on theta, so they cancel out. So finally, in a lot of policy gradient papers, theorems, algorithms, you will see this grad of log pi appear a lot. And the first time I saw that, I was very confused. Where is this grad log coming? And then through this proof, now you understand how do you get this gradient of log probabilities. So intuitively, what we are doing here is that this will help you to imagine what we are doing. So imagine that you are running an agent in any interface, okay? You are generating a lot of trajectories, T1, T2, T3, etc. Let's say 100 trajectories are generated. You focus on each trajectory, T1, and you look at what are the states and actions being, being taken in that trajectory. And then you calculate the log of pi of AT given ST, take the gradient of that, sum it up for this trajectory, and then multiply it by the return. And you do this for all the trajectories and take the mean. That is exactly what would be the gradient of the performance measure. Okay, so afterwards, after this lecture, I'm pretty sure all of you are going to forget the mathematics, but I want you to remember the intuition of this regarding this formula. And the intuition mainly goes in the following lines. You are sampling a lot of trajectories and you are taking the gradient of the log probabilities uh, of the actions taken from all the states of that trajectory, multiplying that by the return, and then you are taking an average over all the possible trajectories. Now, one question that some of you might have is, why is this working? Why does this really make sense, right? Uh, why is it making sure that my policy is moving in the direction of higher rewards? And to understand that, we first uh, need to understand what is exactly happening in this formula. So let me actually show that to you through a very nice example. So I want you to explain this through a very interesting example through which you can understand this analogy. Okay, so I hope all of you can see my screen. So let's say we have this old policy which is denoted by O, right? And we have this new policy which is denoted by N. And this term, grad of log pi AT given ST times G, it gives us the direction to move, uh, the direction to update our policy parameters so that we maximize our performance measure. Now, why does this make sense? Let's say the reward or the return is positive. Okay. If the return is positive, on the right, I have drawn another diagram which is giving the probability of picking action AT when in state ST. Okay, so when the reward is positive, I am moving towards the peak of this mountain, which means that if I sample a trajectory where I'm getting very good returns, I will increase the probability of taking that specific action in that specific state, and I'll move towards the peak of this mountain. But if I get a very bad reward, then I will move away from the peak towards the base of this mountain. I will reduce the probability of taking that action for that given state. So this is why the policy gradient algorithm intuitively works. It reinforces the action if the reward is good, and it penalizes the action if the reward is bad. And the way it reinforces the action is that it increases the probability of picking that action when again that state is encountered. And it decreases the probability of picking an action if the reward is bad when that state is encountered. So whenever you get confused by this log pi, grad log pi, think about this diagram and try to understand for yourself why this particular formula makes sense. So now let us refer to this article to discuss the two things. So here what I was mentioning was, if the reward is positive, you move the yellow dot towards the peak of the mountain, and if the reward is negative, the yellow dot actually moves away from the peak of the mountain and it moves towards the base of the mountain. So now this is also called as the reinforce algorithm, where we have this formula: expectation over all possible trajectories sampled from that policy. And here you have gradient of log pi at given st, sum that all up for a single trajectory, multiply it by the return, and then take average over all possible trajectories. Now, one of the biggest problem with the reinforce algorithm is that it actually leads to a very high variance. And why does it lead to a very high variance? Imagine that you want to find the average age of your country, and you go ahead and collect a lot of samples, and you find out the average. So now this is a difficult problem because your average is going to depend on which portion of the population you have sampled. So if you heavily sample people above 60 years of age, you will wrongly think that the average age of the country is more than 60. And if you sample people lower than 30 years of age, you will think that the average age is less than 30. So you can see how the average is heavily dependent on the people that you sample. Similarly, for reinforcement algorithm or reinforce algorithm, the estimate is heavily dependent on the trajectories that we sample. So this is the example for the population that I showed. The true population is somewhere in the blue. You can see it. It appears somewhere in the background. I'm not sure if you see it properly. And sample 1, sample 2, and sample 3 are the prediction. So you can see how these samples are very different from each other. That is what is meant by variance in the distribution. And that was one of the biggest problems of the reinforced algorithm. And people were for a long time confused what to do with this. And after that, we actually came up with people came up with a solution where they changed this algorithm to something called as reinforce with baseline. And in reinforce with baseline, what happened is that they substituted a value called B of S, which only depends on the state. It does not depend on the on the policy or the action. So if you it turns out that if you subtract a baseline from the return, then that makes a big difference with the variance. And this is something which works with a lot of different problems. If you subtract a constant value, the effect of the magnitude is reduced. For example, if you have a trajectory which is giving a very high output, instead of the policy gradient or the performance measure gradient being biased by that single trajectory, if you subtract the magnitude from that, it will take the actions. It will probably focus more on the uh, credibility of the actions rather than the magnitude of the states and the trajectories which are encountered in that particular trajectory. So this is how the reinforcement with baseline was different than the simple reinforce algorithm. And then people usually what they do is they replace this B of S with the value function itself. So the final formula that you get for this is expected value of trajectory sampled from this policy. You sum it up, t goes from 0 to t, grad of log pi, we are familiar with this now, at given st, and then you add another term where you have g of tau and you subtract it with value function v pi theta of s. So this is something which is, this is a very popular equation. It is called as the actor critic equation, where the return is the actor and the value function is the critique. So this is how the gradient of the performance measure is calculated. People usually do one more small change here. This tau is actually replaced by t, which means that we don't wait till the end of the episode to get the return, but we take the return from that state till the end of the episode. So you can see how we have modified this original reinforce algorithm with reinforce with baseline with just two small changes. First of all, we have included a baseline, which is the value function itself. And secondly, we are not calculating the returns for the entire trajectory, but we are calculating the return from that state till the end of the trajectory, which is g of t. Okay, so this is the final formula that we are going to work with. And now the question is that, okay, what next? How do you estimate how can you make this estimation even better? Because now you can see this as a challenge, right? We have to estimate the return and we have to estimate the value function also. So what people do is that they have something called uh, as advantage function. So the advantage function is denoted by a pi of st given at. And the advantage function measures whether or not the action is worse than the policy's default behavior. So the advantage function is given by the difference between the action value function and the state value function. Okay, so it is denoted by q pi of st comma at minus v pi of st. And we are going to take a simple example to understand this, that what is the exact meaning of the advantage function. So imagine that you have a state S, and from this state S, there are four possible actions, A1, A2, A3, and A4. Okay, and for all these actions, you evaluate the action value function, which is the expected return from that state after taking that action till the end of the episode. So this expected return is, let's say, 25, 30, 50, and 15. Okay, and now what you do is you also evaluate the value function. So let's say your value function for this state, which is denoted by v of s, your value function is, let's say your value function is 40. Okay. Now, if you measure this difference, q of s comma a minus v of s, for the first one, it will be minus 15. For the second one, it will be minus 10. For the third action, it will be 10. And the fourth action will be minus 35. So now what does this mean? It means that all these three actions, A1, A2, and A4, these actions are giving a negative advantage, and this action is giving a positive advantage. Positive advantage means that this action is better than the policy's default behavior, which is measured by the value function, which means that there is still some scope for improving the policy. If all these values were negative, it means that my policy is already optimal. Negative or zero, it means that my policy is already optimal. But the moment you see positive values, you are sure that my agent is probably not taking the optimal actions at every state. And uh, a positive advantage means that you should force the agent to take that action which has, or you should steer the agent in directions where the advantage function has a positive value. And whatever we saw here, this g of t minus v of s, this is exactly same as the advantage function, a pi of st, comma at. So instead of writing two separate terms, people then started representing this entire expression by a of a pi, and they started denoting that as the advantage function. So here I have again explained the same thing. If we encounter a state and action pair for which the advantage is positive, it implies that our policy is choosing some action which is performing worse in the long run compared to the action AT. This means that there is scope for improvement, and there is scope for improving the policy. Okay, now you can see that the gradient of g of theta, it can be simply written as this, where everything remains the same, expected value of pi. There should be a summation here also. T goes from 0 to t. Grad of log pi is same, but we have replaced g of t minus the value function with the advantage function here. So this is how the expression for the gradient of the performance measure looks like at the end. Now, the question is that how do I estimate this advantage function? And that is itself, there is a method for it which is called as generalized advantage estimation. And I'm going to briefly explain that for 5 minutes. It is completely understandable if you feel free to skip this explanation and don't understand this properly, because that is not really required for us to understand the entire RLHF pipeline. So I'm going to quickly go through this, but try your best to understand as much as you can grasp. Okay, so we want to estimate the advantage, which is the difference between the action value function q pi of st comma at and the state value function, which is v pi. And the action value function is denoted by expectation of cumulative rewards received by the agent from the current state till the end of the episode. And this itself can be written in such a way that you take this current reward out plus gamma times expectation of RT plus 1 plus gamma RT plus 2, etc. So it can be written as the current reward plus the discounted next value, which is V pi of ST plus 1. So through this mathematical improvisation, you have replaced the action value in terms of the state value. The only catch is that the state value is for the next state, which is ST plus 1. So now we can use RT plus gamma times value function of the next state as a proxy for the action value function. Okay. Now, this is called as the one step backup, because we are taking the reward and adding it to the value of the next state, and we are looking one step ahead. So using the one step backup, the advantage estimation can simply be written as this. Advantage is RT plus gamma times value function of the next state minus the value function of the current state. Now we can be happy with this and we can say that, okay, fine, this is the advantage estimate. And let us use this in our gradient of the performance measure formula, and let us calculate the advantage using this estimate. But then you can see that this is biased. We are only using one step backup. The natural question is that what if we use a two-step backup or a three-step backup? That would reduce the bias because we are now looking multiple steps ahead. If you do a two-step backup, the Q estimate will look like this. the current reward plus the discounted value of the next reward plus the discount plus gamma square times the value function of the next to next state, which is st plus 2. And so the advantage function can be written like this: rt plus gamma rt plus 1 plus gamma square v pi of st plus 2 minus v pi of st. And similarly, we can do a n-step backup also. So we can do either a one-step backup or a two-step backup or a n-step backup. So we have multiple options. Now, to reduce bias for any of this, what people do is that they do a combination of this. Let's say I do half of a one-step backup and half of a two-step backup. Then the Q estimate will look like this: half of RT plus gamma times V pi st plus 1 plus half of RT plus gamma RT plus 1 plus gamma square V pi of st plus 2. Now, then the advantage function will look like this. But now the backup diagram is given as follows. So more generally, in a complex backup, here we have only considered one-step backup and two-step backup, and we have combined them. Now you might think that, why did I only consider two-step backups? Why don't I consider an n-step backup, right? So that is exactly what is done in practice. People usually, this diagram looks a bit messy. Let me clear this up. Okay, people usually use weights which are like this. 1 minus gamma is the weight associated with the one-step backup. 1 minus gamma times gamma, 1 minus lambda times lambda is the weight associated to two-step backup. 1 minus lambda times lambda square is the weight associated with three-step backup, and so on. Okay, now if you add this all up together, the weight given to one-step return is 1 minus lambda. Weight given to the two-step return is lambda times 1 minus lambda. Weight given to the three-step return is lambda square times 1 minus lambda. And then you add this all up together. So then this is how your advantage function is written. So this method is called as the generalized advantage estimation. And what we are essentially doing is that we are using a composition of one-step return, two-step return, n-step return, and this composition is represented as a part of another variable which is called as lambda. Okay, so now as a part of this lecture, I really don't want to focus too much on the specifics of generalized advantage estimation or GAE. For now, in the last 30-35 minutes, the overall summary that I want to give to all of you is the final formula for the gradient of the performance measure looks like this. Okay, where we are taking the expected value over all possible trajectories and we are multiplying the advantage by the gradient of the log probabilities. And why this makes sense is that if you have actions which have a positive advantage, it means that you are going to be traversing up the mountain, you are going to increase the probability of choosing that action for that specific state. But if your advantage is negative, then you are penalizing that action for a specific state and you are moving down the probability mountain. So that is why this policy gradient theorem intuitively makes sense. Okay, so now that we have understood this, finally, let's look at the final formula that we have developed for the policy gradient theorem, which looks as follows. Okay, so now the main challenge for all of us is going to be, this is fine, but how do I represent all these terms for a large language model? And this is exactly what we are going to focus on in the remainder part of the lecture, so that every single term in this expression will be explained with a complete clarity to all of you. So let us understand what each of these terms mean for an LLM. First, let us take an example and we'll stay consistent with that example throughout this explanation. So the example prompt is, where is Pune? And the answer is Pune is in India. Okay. So now first let us map this to a trajectory of states and actions. You might have already guessed how we are doing this mapping. States and actions. State S0, where is Pune? Action A0 is Pune. State S1 is where is Pune? Pune. And action is A1 is. State S2 is combining the prompt with the previous action, with the previous set of prompts which have already been predicted by the LLM, and then taking the next action, which is A2. The last state S3 is combining the prompt and whatever tokens have been predicted, Pune is in, and the last action is India. So this is exactly how we construct the state action pairs for a particular trajectory. So I'm using the word trajectory, and I'll continue to use this. Uh, when I say trajectory, I mean that when we have a combination of prompt and answer, we have to map it to a trajectory of states and actions, because that is exactly what we need in our formula for the gradient of the performance measure. So we have S0, A0, S1, A1, S2, A2, and S3, A3. That is excellent. But now we have to calculate the log probabilities. Remember, here we have log of pi of AT given ST. So how do we calculate that? Log of pi of A0 given S0, for example. So this answer all of you already know, and let's try to understand this, how it's calculated. So this is the figure which I had showed you in the first 25 minutes of today's talk. This is how a large language model works. So what happens is that you pass in the prompt plus the answer. Where is Pune? Pune is in India. And first it goes through the transformer block. It goes through the input block, then it goes through the transformer block. Then we have these hidden states, which remember had 768 dimensions. And then you project this into the vocabulary space and you get the logits. And then you apply a softmax here. And then you calculate the probability for all these logits. Okay. Now what we are interested is, this is A0. This is A1. This is A2. And this is A3. Now, this is what is log pi of A0 given S0. Sorry, I'll again explain that. This is the log probability of all the possible tokens in the dictionary. Out of that, we select the log probability of the token which is Pune. So then you get log pi of A0 given S0 here. Similarly, here you get log pi of A1 given S1, and then here you get log pi of A3 given S3. So these log probabilities are already known to us because this is exactly the way our LLM works. And this is why policy gradient becomes very naturally applicable to large language models, because the log probabilities are already calculated after the logits. It's very easy to calculate this. And you get the log probabilities of all the tokens in the vocabulary, remember, but now you have to calculate the log probabilities only for the selected actions. Okay, so we get 4 log probabilities, and now we have this terms ready with us. We have log pi of A0 given S0. We have log pi of A1 given S1. We have log pi of A2 given S2. And we have log pi of A3 given S3. So if you look at our formula, this is one major part of our formula which we already know actually. Okay, so now once we have calculated all this, we have to now go ahead and see how we can calculate the advantage function a pi. Now what I am going to do is, for today's lecture, I am going to explain to you. Okay, so first of all, before we got to the advantage function, you might be remembering that we had another term here which was called as g of tau, which was the return from that trajectory from the start till the end of the episode. And then after this we said that okay, fine, so this is giving high variance, so let us change this to API. So today what we are going to do is, today we are going to stick with this original form of, we use a different color, this original form of the policy gradient, which is also called as vanilla policy gradient. So in the vanilla policy gradient, what happens is that we do not need to calculate the advantage at all. We only need to calculate the return from the start to the end of the episode. And all of you might have already guessed how this is calculated. We had discussed about the reward model previously, right? So when you pass this through a reward model, you get a reward. So let me again explain that so that you understand it properly. Okay, so now what we are going to do is that we are going to replace this with g of tau, which is the expected, or which is the return which is received at the end of the trajectory. And how is that calculated? Let us go back and look at the way we had uh, drawn our reward model. Okay, so remember this. This is how we had drawn our reward model. Now we have the same prompt. Where is Pune? Pune is in India. This is our trajectory. Now the question is that how do we calculate the expected return for this trajectory, right? So when you pass this entire trajectory through this reward model, finally you are going to get some value like 15. And this is going to be the g of tau, which is the return for your model. Now, what people do is that this return is received only for this last hidden state, because when you pass a sentence to a reward model, you do not get returns for all the individual tokens. Why is that the case? How will you evaluate the reward for where is, or where is Pune, or where is Pune Pune? You can only evaluate a reward when your trajectory is complete. But what people do is that this same reward is then assigned to all of these state action pairs. Okay, so what happens is that a reward is calculated for the last state, which is the entire prompt plus the answer. And then that reward is assigned to all the previous states which are encountered. So let me actually draw it here. So here now let's draw the rewards. First, the reward is calculated for this R3. Okay, so this reward is whatever the reward model gives you. Let's say this is 15. So then R2 is also 15, R1 is 15, and R0 is 15. And these are the values which are substituted here. So by mistake, I have given g of tau here. It should be g of t actually, not g of tau. Okay, so this is how we are going to estimate our gradient of the performance measure. Now, I hope you can understand how all these values are available to us. We already saw how this is available to us, and now instead of advantage, we are today looking at vanilla policy gradient. So we know how this value is available to us. Tomorrow we are going to, or in the next lecture of in this RLHF workshop, and we are going to look at how this advantage function is calculated uh, for uh, or using our reward model. But for now, in many cases, even vanilla policy gradient works fine. So we are also going to look at a practical example to see how this exactly works. But this we have obtained, and this also we have obtained. So we are all set now actually to calculate this gradient. And some of you might be wondering how this gradient itself is calculated. So this is very similar to how we calculate gradient in any typical machine learning problem, where we run gradient descent methods, and using back propagation, we calculate the gradients. So I'm going to show you this with a practical example. But before we get to that, I hope all of you understand this. Now, there is one last step which we are yet to understand, and that is called as reward hacking. So what exactly is reward hacking? Let's say our reward model is trained to give positive rewards to happy sentiments and negative rewards to sad sentiments. So during the RL training, our LLM might just hack the reward. This means that LLM might figure out that using happy or love or thank you is giving more rewards and start using more and more positive words without understanding the context. For example, if you see LLM give just love, love, happy, this does not mean anything, right? But this will possibly give you a very high reward because you're giving high rewards for happy sentiments. And we don't want this to happen. We don't want our LLM to hack the reward, right? We want it to actually give rewards to sentences which have positive meanings, and the context also should make sense. It should not be just a random group of words which our LLM uses. So we need to prevent this from happening. And we need to prevent our model from deviating too far from the reference model, which actually works decent. So usually the reinforcement learning step happens on top of a already trained LLM, which is quite decent at doing tasks. So we do not want to completely change that. And to avoid that, people measure the difference in the log probabilities of the same token predicted by our language model and the frozen model, which is the reference model. And this is done by a metric which is called as the KL divergence. So for two distributions, P and Q, the KL divergence is denoted by this, and it denotes how different these distributions are from each other. So if we get a log probabilities which is very high, or the differences in the log probabilities from our current model to the frozen model is high, then we basically penalize that reward. So this is how our reward is finally calculated. This is the actual reward which we get minus the KL divergence of the policy and the frozen model. Now, how is this KL divergence calculated? You might have to just turn your eyes a little bit to look at this. So this is the same transformer block which we looked at before. And this is the same for the frozen model. We have taken the same example. Where is Pune? Pune is in India. And here we have calculated the log probabilities. Now let us look at this or one such case where the log probabilities by the frozen model and the log probabilities by our trained LLM, and we calculate the KL divergence between them. And that is subtracted from the reward. So essentially what we are doing is here, when we saw R0, this is actually subtracted from KL, one KL divergence term between the frozen model and the the current LLM which is being trained. And this is something which all of you should be able to understand now, how we are taking the difference between the log probabilities, because we already have the log probabilities with us for the currently trained LLM and the frozen LLM also. So it's a very nice way to compare whether the current LLM is deviating too far from the frozen LLM or not. So the reward model is then then the reward is just a subtraction of two terms. The first term is the reward which is calculated by a reward model, and the second term measures the KL divergence between the policy and the frozen model. Okay, now enough theory. I know all of you are waiting for some practical example, and I believe that theory can only take you so far, but the final implementation should always be practical, so that whatever theory we have discussed, there is a nice way to apply that theory so that we can see an example being built. So now what we are going to do is we are going to actually fine tune a large language model to align our output towards positive sentiments. So we are going to build an entire RLHF pipeline from scratch. And what we'll do is, I will share one GitHub repo with you. Some of you might, it's the same repo that we have been using for our hands-on RL bootcamp. So all of you can head over to this repo. So someone has asked, what is the meaning of frozen model? So the frozen model is usually the reference model that we start out with. When we are fine-tuning the LLM using reinforcement learning, we start with some model, right? That is what is the frozen model. I will explain that more in detail once we cover the practical example. So you can clone this repo and you can head over to this folder, which is named as RLHF Part 1. Okay, so let us get started. So what we are going to do is that we are going to develop an entire RLHF pipeline to fine-tune a GPT-2 micro model to align our output towards generating positive stories. Okay, so we want to generate tiny stories, but with positive sentiments. And we are going to use RLHF to align or to steer our model to generate positive stories. So let's first understand the entire process and the pipeline. So we are going to use a tiny model, which is GPT Micro. And this model essentially has 4 layers, 3 heads per layers, and 128 is the model dimension, which was the same I was talking to you about 768 dimensions, right? Which is the hidden size. So here it's 128. This model has around 1 million parameters. I've chosen this model so that all of us can run it easily on uh, even a single GPU if available. I'll explain the training procedure as we go along. For now, just remember that we have the architecture of a GPT micro model, which is 4 layers stacked on each other, but we have not done any kind of pre-training yet. This is the data set which we are going to use for pre-training. I'll share the, or you can just type tiny stories Ronen Eldan on Google and you will find this data set. So this data set has around million stories, and we are going to do the pre-training also. Remember, pre-training is where the token is passed through the entire LLM journey, and then the weights are updated so that the actual or the predicted output matches the actual output. So we are actually going to even do the pre-training process in this practical demo. So you can consider that currently the GPT weights are random, it does not know anything. But after pre-training, you will see that it slowly starts to create these tiny stories. There was this wonderful paper released by Microsoft on tiny stories, through which we got this idea of using this example for for RLHF. Okay, so the methodology is that we are going to be performing these following steps. The first step is, as I mentioned, we are going to pre-train a model from scratch using the tiny stories dataset. Then the second method, which is usually quite popular, before we do the reinforcement learning step, people always do a step which is called as a supervised fine-tuning. So we are going to do this step of supervised fine-tuning. And for this, we are going to fine-tune our pre-trained model using positive stories from the tiny stories dataset. Now, some of you might be wondering that why do you need this SFT stage? Why can't I directly, jump from pre-training to RL? And this actually comes from this paper, which is fine-tuning models from human preferences, where you can see there is a very nice table towards the eighth page, where they have clearly shown that using supervised plus RL fine-tuning leads to much better accuracy. And from there on, it has become an industry standard that before you start with the reinforcement learning step, you always have to do the supervised fine-tuning step. So we are going to fine-tune the model using a set of stories selected from our original data set, which are positive in nature. And then we are going to use reinforcement learning step. Now here you might notice that the reinforcement learning step, the reward model that we have constructed for this, it is not a reward model based on human preferences, but we are using verifiable reward. So this process is also known as RLVR. So in fact, in DeepSeek, they have used RLVR significantly compared as opposed to RLHF. But anyways, we are going to cover human preferences data also in the next lecture. For now, just focus on this reinforcement learning step with rewards which are verifiable. So how do we verify whether a story is positive or negative? We use a sentiment analyzer for doing that. So if the sentiment analyzer model gives very high score to a story, it means that it has more and more positive sentiment. So that itself becomes the reward. So we do not train a reward model specifically from scratch, but we use a sentiment analyzer, and that itself becomes our reward model. Now what we'll do is we'll first look at the reinforcement learning step and try to see whether what we have learned in theory is that really closely matching with what happens in practice. And I want to establish a very close mapping, because sometimes it happens that we learn something in theory and then in practical people do something completely random. So there is a gap. So here let's make sure that we are understanding everything. So when you open the GitHub repo, you will see a file called as tinystoriesgpt.py. And within that, there are some sample of code, which is in the RL step I'll go through now. So there is a code where we are sampling trajectories, and this is the code where we are doing that. So let me zoom on to this. So this is where there is a command which says model.generate prompt. Okay, maximum new tokens is the block size, temperature, do sample, etc. But this sentence basically generates multiple trajectories. Remember in the gradient, you had this trajectory sampled from pi of theta, sigma t goes from 0 to t, grad of log pi, at given st, multiplied by g of t. Right? So here you have to sample a lot of trajectories, and for all these trajectories, you have to calculate this. And this is exactly what happens here. You pass in a prompt, which is uh, just a start of a sentence, and you ask the model to generate the entire trajectory. And this is how the trajectories are generated. So in the code, it is mentioned how many trajectories are generated, but there are, I think, 30 to 40 trajectories generated per iteration. Okay, and now this is where the trajectories are sampled. Now, how to calculate log probabilities of the actions? Remember, we have discussed this in length, how this is calculated, but let's try to see. It's actually very simple, just one line of command, and you might struggle to understand this at once. What is this thing that is happening? So this thing, right? Completion, comma, colon -1, completion, colon, comma, 1, colon. What this does is that it basically shifts the index by 1 and creates states action pairs and then calculates log probability. So I have given an example at the bottom to help you understand this. Let us see why this works. So let's say completion is this. Where is Pune? Pune is in India. And when you shift this by 1, basically what you get is you get a set of input output pairs. So maybe if I write this in a separate table, it also becomes your states and actions pairs. So now I have shifted this by 1, right? You can see this line is shifted by 1. So now where is corresponding to is. Okay, then where is corresponding to Pune. Then where is Pune is corresponding to Pune again. Then where is Pune? Pune is corresponding to is. And then last one, where is Pune? Pune is in is corresponding to India. So just by shifting the completion by one, you get the input output pair. Now, what happens here is that first you calculate the log probabilities for all of these states, right? Let's say you first calculate the log probabilities for um, all the tokens projected from this state, and then you select the log probability for this token. Then you calculate the log probabilities for this and project it out in the vocabulary and only select the log probability for this token. So it's astonishing that with one single statement you can do that. But what's basically happening is that this first thing, this is generating the log probabilities for all the possible actions for that state, and this is selecting the action which the model has picked. So this is exactly what we are doing. And remember, completion is already defined before here, is what the model is generating for us. Okay, so now once the log probabilities are generated, we have this, we are ready. We can calculate the rewards. Now, reward is calculated by reward model. This is simply a sentiment analyzer in the code. But let's assume for now we have the reward model. So the reward model is calculated. Now here, what we do is, remember that similarly as we calculated this log probs, we also calculate log prob for this reference model. Is the same line of code essentially. Ref model dot log probs completion index shifted by one to generate the input output pairs. But the only difference is that this is calculated for the reference model. And then we calculate the KL divergence, which is the difference between our current model and the reference model. We multiply it by a parameter called KL beta, give a minus sign, and then add it to the rewards. So the final reward is stored in the score function, which is score equal to score plus rewards. So here what's happening is that input is this, right? It has all these states S0, S1, S2, S3, S4, S5. And the KL divergence is minus KL0, minus KL1, minus KL2. These are all different values. Now, when you pass this completion through the reward model, you only get one single reward. But that same reward is propagated back and given to all these states. So the final reward then becomes R minus KL0, R minus KL1, dot, 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 R minus KL5. And this is done through this line. So this is exactly what we saw in the theory, that first we take the KL divergence and then we subtract it from the reward, and the reward is always calculated at the end of the sentence, right? And then that reward is the same reward which is given to all the input tokens in the sentence. And then finally, the last step is to train with the policy gradient method. Now, this is where we utilize the formula. Here you see log probs and the score. So this is basically log pi of AT given ST multiplied by G of T. And here we are taking the mean, so that takes care of the summation part. T goes from 0 to T. And because we are sampling a number of trajectories at the top, that takes care of the sampling part. So finally, we have this formula. And then we do a backward propagation with this and optimize it using, these are very similar steps which are used in traditional machine learning optimization, where you run a gradient descent algorithm in this case. So that's why we have a minus sign here, because the formula that we had was for maximizing the performance measure, but Here it requires a performance measure that we have to minimize. So that's why a minus sign is attached over here. So that measures the loss which we want to minimize. So that's it. Now what we'll do is we'll move towards the code section to understand how all of it works. And I want all of you to actually implement this so that you get a lot of satisfaction in this whole process. So this is the code. Uh, Scroll down, I'll explain the part which is above. First scroll down and here focus on this part which says starting reinforcement learning. So this is the exact same thing which we have seen as a part of the code now, where this was the vanilla policy gradient loss. This was where the reward model was calculated. This is where the trajectories are generated. So let me zoom in a little bit so that you all, yeah. Okay, now what we'll do is we'll start from the first step in the code, which is slightly at the bottom. We'll start here. This is where it says starting pre-training on tiny stories. So the data set that we have loaded is this tiny stories data set. You can click on this and have a look at the data set, but we are doing the complete pre-training from scratch. And we are running it for one single epoch. And you can see over here at the right, if I can show it to you, when you run the pre-training, we will see a graph which is generated, which actually shows you how the, yeah, so after the pre-training, you should see something like this, that you run for 15,000 iterations and the training loss decreases and the validation loss also decreases, which means that our model is able to generate good, like coherent stories. And let me actually show you how those stories look like. Okay, so once you start generating, right, once you start doing the pre-training, you will see something like this. Uh, yeah, pre-training starting pre-training on tiny stories. And initially you can see it at step 0, it generates some gibberish. And then after some time, it starts to generate coherent stories. Once upon a time, there was a little dog named Spot. Spot was a very big box. And so it makes mistakes, right? Because it's still early in the training. Then towards the end, you can see at 15,000 step, it's pretty good. Once upon a time, there was a good boy named Joe. Joe loved most of his family and sitting a cashier. Also, slightly, it's not able to do well. We have, but it overall it generates sentences which are largely coherent. We have used a small model here. So if you run this, you can see that the loss reduces around to 0.3 and or 0.4. Now, before you run this code, I have given some instructions in this README. So first, what you can do is you can execute all these instructions, something related to package dependencies. You might have to install this version of NumPy, uninstall ContourPy, and then in the latest version of the README, I have also given instructions like I think two instructions were missing in this, which was pip install NLTK and also leader lexicon. So sorry, Vader lexicon. So now what happens is that in after that after this pre-training is done, we move to the supervised fine-tuning stage. Now in the supervised fine-tuning, you can see that the way we have created this data set is we have used this function story dataset and filter sentiment is equal to positive. So what we are doing is that we are looking at all the stories and then we are filtering it to check stories which are positive, and that function is given over here. So this is a function where we are detecting the sentiment of the story using the sentiment intensity analyzer. And then we are classifying whether the story is positive or negative. So when you run this code, you will see that this process takes some time, because this is important for us, because for supervised fine tuning, we should not select stories which have a negative sentiment. We should only select stories which have a positive sentiment. So this allows us to do that. Okay, and then the SFT stage will run and you will see a graph which looks something like this. Yeah. So initial loss will not be very high because you have already done the pre-training, and then naturally you will see the loss going down. Probably if I run this for more epochs, the loss will slightly go down more, but I don't think it will go down by that much. And then after that, you start the RL stage. Now the question is that how is the reward model constructed? So let's look at it. Okay, so this is the sentiment reward model where all you are doing is that you are using this sentiment intensity analyzer to assign a score to your sentence, and that score becomes your reward. So it's called a verifiable reward because you are using a tool to give rewards to your trajectories. So we have not used human preferences reward for this specific case, but we will look at that in the next lecture. For now, just understand the overall theory, what we have done here, how we have used the reward. And once you do the RL training, you should see graph which looks like this. Now, this graph is actually very good because you can see the training is or the reward is slowly rising. That means that our policy gradient algorithm is actually working. And once all of you see this, you will really start to enjoy this the entire theory behind RLHF and how reinforcement learning can be used to fine-tune language models. So that is the broader umbrella which we are working with today using RL to fine-tune LLMs. And for that, there are three steps: pre-training, SFT, and reinforcement learning based fine-tuning, which can either be through human feedback or using verifiable rewards, which is exactly what we are doing today. Now, the good thing here is that once you have done this, you can actually run this file which is called app.py, and let me actually run it. And you will see an application running. You can customize the front end completely, and you can get interesting looking interfaces. But if you run this Python app.py, you should see browser load up where you can see the difference. So let's say I write an ugly or unicorn stumbled upon, let's say, and then I click on generate story. So you will see two blocks. First is the output given by your pre-trained model, and second is the output which is given by the model which is fine-tuned using reinforcement learning. And you can see a clear difference here that in the RL fine-tuned model, it uses a lot of positive sentiments. So here it's using sentiments like liked, loved, liked. And in this case, the difference is only one. There is 2 and 3 here, but in a lot of other examples, the RL fine-tuned model works very well. So let's consider another example. Uh, So in some cases, what happens is that the pre-trained model gives some sentences which sometimes don't make sense. But yeah, here you can see it's formatted also wrong. But our RL fine-tuned model, she loved to play in the garden with her mom. One day they needed to go outside and play. He loved to ride his bikes and unpack, play with cars. One day he saw a big blue dog with a red car. He loved to play with his scooter. He liked to explore. So you can see that it has understood to use words like liked, loved, happy, beautiful, etc. And this is a proof that it has really understood that I want to steer towards sentiments which are more and more positive in nature. So all of you, it's very important for you to be able to successfully run this code so that you develop the confidence to train RL model. This will not take a very long time to run. You probably need a GPU. You can run this on CPU also. For me, on a GPU, it took around 2 hours to run. I was using think an A40 GPU. So yeah, if I'm not wrong, it did not take much time, around 1.5 to 2 hours, and I was ready with this. So all of you, once you have done this, it will be great if you can share your interface on LinkedIn so that others can also get an understanding of how reinforcement learning can be used to steer LLMs in the right direction. So so now what we'll do in the next lecture is, so this brings me to the end of today's lecture. We covered a lot of things. We'll not be covering, let's say, in the next lecture, we'll cover how to use human preferences and build reward models from human preferences. We have already seen how to construct a loss function for that, but we haven't seen how to use that in practice. And we'll also cover proximal policy optimization. That is one of the core algorithms which is used in modern RLHF implementations. People don't really use vanilla policy gradients that much, but in some cases it works fine. So there is no real need to go to PPO related methods. So, and then we'll also look at excellent libraries like OpenRLHF, which provides a framework for running RLHF implementations at scale. So let's say you are looking to fine tune a model like Llama 7 billion, or even a small language model. You have a specific, let's say you have collected human preferences from a therapist or from someone, and you want to steer this model towards those responses. So applying reinforcement learning to small language models is, I think, the future. Not a lot of people are focusing on it. But the reason it's important is because the advantage of SLMs is that you can build small language models specific to a domain. You don't need billions of parameters. But then it's important to align these SLMs also towards human preferences. Just take an example of, let's say you build a chatbot which gives you, let's say, therapy-based answers. Let's say you want to go for a therapy and you go to a chatbot, it gives you responses. So you build an SLM for this, but let's say you want to give responses in a particular style or in a particular preference, then without RLHF, you will end up with a chatbot which is very generic. It will give average responses based on whatever it has seen in the data. You can't really align it with your own preferences. So this becomes a very important step in the whole pipeline of pre-training and fine-tuning an SLM. Typically, it will involve three steps. One is pre-training, SFT, and finally it will end with RLHF. So if any one of you are interested, there are I mean, these are open-ended problems which you can take care of. The next lecture will be conducted next week on the next Friday, and we'll cover both these. We'll cover PPO also, and we'll cover how to use reward models with human preferences. And then towards the end, we'll also touch upon using OpenRLHF and how to use frameworks like Ray and VLLMs to take care of like bigger models to train. Okay. Thank you, everyone. Uh, it was a very extended lecture today, but all of you have stayed patiently. I'll be uploading the lecture also on the dashboard. Thanks, everyone. All the best. Bye. So, in the last lecture, we started looking at how reinforcement learning can be combined with large language models. And the combination of the two itself, we realized, was not very straightforward, because reinforcement learning problems can be represented as agent environment interfaces. And it was not very clear for us in an LLM what is the agent, what are states, what are actions, and what are rewards. But then later we slowly and steadily understood that the states are nothing but the prompts which are given to the LLM, or in a more technically correct way, let's say you are giving a prompt to the LLM, I am going, then the state is all the words or tokens which have appeared before, and the action is the next token that is predicted by the LLM. Okay, so let's say the LLM is starting its completion. So first the state is the prompt itself, then it makes the first prediction, which is the first token, that is the action. Then the prompt plus the first token which is predicted by the LLM, that becomes the state. Then it takes one more action, it predicts the next token. Then the prompt and the first two tokens combined, that becomes the state, and the next token predicted becomes the action. And we have written this down here. The question is, where is the dog? And the answer is the dog ran away. So initially the state is S0 is just the question, A0 is the, and then as you proceed, uh, S1 is Q and the, and A1 is dog, and then similarly you can write all the state action pairs. So this is also something which we called as trajectories in the last lecture. One single trajectory means a series of these state action pairs which are generated by the LLM when it generates an answer. Okay, so states and actions are clear, but we saw one more puzzling thing, and that puzzling thing was that when we are looking at LLMs, the agent is the LLM, that is fine, but the policy is the same as the agent itself. And the reason is because the definition of the policy exactly matches with the definition of the LLM. The definition of the policy is policy tells you the probability of taking an action for the current state of the agent, and the LLM also tells you exactly that. The LLM is telling you the probability of choosing the next token with the maximum or it gives a probability distribution of all the tokens, and then you select the token with the maximum probability. So okay, so because the definitions match the definition of the policy and the definition uh, of the LLM, when you represent large language models as agent environment interfaces, the LLM is same as the policy itself. Okay, so let's move on to the next section. Now, once we have understood what are the states, what are the actions, and we have understood that the LLM itself is the policy, the next question is, what are the rewards? How do we define the rewards exactly? And we actually looked at a very interesting way of defining the rewards, and we did not look at a practical example of this. We will look at that in today's lecture. But the first intuition that we built was that if you ask a question, what is 2 plus 2? And the LLM gives the answer as 4. So here I know that the reward is going to be high because it's very easy to verify these kind of questions. You can verify using a calculator that whether 2 plus 2 is equal to 4 or not. But then there are some other questions like explain RLHF like I am a 5-year-old, whose answer is very subjective in nature. For example, some of you might like this answer given by the LLM, some of you might not. So then how do you assign rewards to questions which are subjective in nature? And this is something which actually puzzled people for quite some time. And then the answer comes from thinking very logically. Humans are not good at finding a common ground for agreement for subjective questions, but we are good at comparing. If I am given two different answers, I can easily tell that, okay, fine, answer A is better than answer B, or answer A is bad than answer B. And that is exactly how the reward are going to be constructed. So here we took another example where the prompt is what is 2 plus 2, and answer 1 is 36 and answer 2 is 4. So I can easily say that, okay, answer 2 is correct. It's better than answer 1. Similarly, if I ask the prompt who is Donald Duck, then I know that answer 1 is the preferred answer. How do you teach RLHF? For me, answer 2 is the preferred answer compared to answer 1, etc. So this way you can intuitively tell that if you are given uh, two different answers, you can easily give your preference. So now, okay, fine, this intuitively makes sense, but how do we assign one number to this? How do we assign one number to a prompt and the answer which is given by the LLM? And to do that, we are going to construct something called as a reward model. The reward model takes the prompt and the answer as an input, and it gives one single number as the output, which is the overall reward for that entire completion, which is the prompt plus the answer. So this is another terminology which I'm going to use in this lecture. I'm going to use the word completion for prompt plus the answer which is given by the LLM. Okay, now the question is, how do I construct a reward model? Notice that I have used the word model here. Model means that I am developing something which can give me some approximation to the reward. It's not going to be exact, but later I'm going to use that model to predict rewards for other questions which my model has not seen while training. Very similar to where in machine learning you use a lot of training data, train the model, then you discard the training data when you are testing the model. So similarly, we want to construct something which can help us give a quantitative number to subjective questions also based on the priorities or the preferences given by humans. So let's look at how we can do that in the first place. So the reward model is actually built from the LLM architecture itself. And in the last lecture, we looked at the journey of a token through the LLM architecture. And through that journey, we understood that the LLM architecture is divided into three components. There is an input block, which assigns the token embedding and the positional embedding to the token. Then there is a transformer block in the middle, which has a lot of different compartments like attention heads, MLP layers, multi-layer perceptrons, then dropout layer, normalization layer, etc. And then towards the end, you have an output layer, which maps the hidden states to the vocabulary. Now, in the reward model, the only difference is that you remove that output layer entirely and then you assign one single reward. So I'll just remove this for clarity. So here what you do is that you assign one single linear layer to the last hidden state, and then you predict one single scalar value as the reward. So this is how we are going to construct the reward model. It's going to have a very similar architecture as the input and the transformer block exactly remains the same, but the output block does not have the projection to the vocabulary. Instead, it projects the output to one single scalar value. Now, in the last lecture, we did not look at an example of this. Remember, because we used a sentiment classifier to predict our reward. So we did not use an LLM based reward model like this. But in today's lecture, we are going to actually look at a practical example which uses a reward model which looks something like this. So if you are having some doubts with respect to this right now, you are not able to visualize this properly, no problem. It will become clear as we go ahead. The main question is that how do we define the loss function for our reward model? How do we train the loss function? And you might have guessed that the loss function is defined based on the preferences given by the users. So for example, uh, if I ask the prompt what is 2 plus 2 and answer 1 is 36, answer 2 is 4, then the reward for prompt and answer 1 is 2.5, reward for prompt and answer 2 is 6, which is good because the second answer has a higher reward. But look at the second example. In the second example, answer 2 is getting higher reward compared to answer 1, which is bad. So intuitively, what we are doing is that we want the difference between the reward for the chosen answer and the rejected answer to be as high as possible. First of all, this difference should be positive, and secondly, this difference should be as high as possible. And with this intuition, we construct a loss function which looks like this. It looks like this: minus log of sigma, reward given for the chosen answer minus reward given for the rejected answer. Now, this might confuse you a little bit how this works, why exactly this works. And we discussed this in the last lecture that let's say there are two cases where the chosen reward has a very high value compared to the rejected answer, which is exactly what we want. The chosen answer has a high value compared to the rejected answer. Now, which means that this difference is positive. And when you apply the sigmoid function to an input which is positive, the answer is going to lie between 0.5 and 1. And if you take a log of that, it's going to be a very small value in this region. But now let's say case 2, your chosen answer or your chosen answer or preference gets a low reward compared to the rejected preference or answer. This is not at all what we want. Now, in this case, we want the loss to be very high, right? Let's see if that happens. If the input to the sigmoid is negative, the answer or the output from the sigmoid is going to lie between 0 and zero point 0.5. And if you pass that to the loss function, you get very high value. At 0, it is infinite, but 0 to zero point 0.5, it's very high, which is exactly what we want. That is why this loss function makes sense. Again, in the last lecture, we did not see how we are going to train this reward model to minimize this loss, which we are going to look at today. But for an LLM to be viewed as a reinforcement learning problem, the states and actions and policy are straightforward. The only difference is the reward, which is the reward model in this case. In most of the common examples of reinforcement learning in robotics, video games, the reward is very clearly defined. You don't need to construct another model for it. But for LLMs, it's not as easy because many times the questions are subjective in nature. So we don't have a clearly defined reward and we need to have a model in the first place. Now, there are some critiques which people have nowadays that why do you need a reward model? Isn't it a very crude approximation? And there are some workarounds to that. There is one algorithm which is called as DPO or direct preference optimization, which completely gets rid of this reward model. It does not have any reward model. And the title of that paper is actually interesting. If I'm able to recall correctly, it's something like your LLM is secretly a reward model in itself. So we are not going to look at DPO in our course, but you can just read up on it. The paper is very nicely written, and there is a blog by this person called Cameron Wolf, which is excellent. In that blog, he nicely summarizes everything about DPO. The main crux of DPO is that the formula remains exactly the same, but here the R is predicted by the LLM itself. It's not given by an explicit reward model. So I just want you to keep this in mind that uh, for our purposes, we are going to use the reward model, but it is not mandatory to have a reward model for uh, aligning your language model towards human preferences. There are other methods like DPO out there. Okay, so now in the last lecture, we also looked at to understand RLHF from first principles. We learned about policy gradients. And finally, we came up with this formula where we saw that the gradient of the performance measure is is given by the expectation over all the trajectories. And what are we calculating? We are calculating the gradient of the log probabilities of all the actions multiplied by the advantage function. Now, why this intuitively makes sense is that basically, if let's say you get a high advantage means that the action which I am taking is better compared to the policy's default behavior, which means that I want to increase the probability of taking that action whenever I encounter that state next, which is exactly what happens. If advantage is positive, the gradient is going to push the probability of this action in a direction where whenever this state is encountered, this action is going to be performed by the agent in that state. This is what this expression intuitively means. And in the last two lectures, we have seen this so many times now, you might have gotten used to this grad log pi into a pi, which is the advantage multiplied by the gradient of the log probabilities. Now, our main focus in these RLHF lectures is how do we apply this for language models, and our entire effort has been towards that direction basically. So, after our last lecture, I wanted to give you a very nice visual representation of how exactly are these log probabilities calculated. And to do that, I have developed a RLHF visualizer module, which I think will really help you understand this process. Okay, so right now I'm going to show you two blocks. At the bottom, you can see there is a block for token shifting and there is a block for log probabilities. So I want to help you understand how exactly are these log probabilities calculated. But before we go to the example, What we are doing here essentially is that if the prompt is where is Pune and the answer is Pune is in India, first thing we do is we map it to a trajectory of states and actions. So for the state where is Pune, the action is Pune. For the state where is Pune, the action is. And then we move on in this direction. So first we create state action pairs and then we calculate the log probabilities. But before we go to this diagram, I first want to give you a very nice representation of how this is done. And there are some this is done in 3 lines of code, and I'm going to explain how this is done. So this is the first line of code where you generate a completion. So model dot generate prompt. So here the prompt is where is Pune and the response is Pune is in India, and the completion is the prompt plus the response, which is where is Pune, Pune is in India. Okay, so this is what the completion array contains. Now so far so good, we are clear with that. Now, how do you generate input output pairs from this completion? The way you do that is that firstly, you tokenize this completion. You assign tokens to each words like we have done here. There are tokens assigned to where is Pune question mark etc. And then after the tokens are assigned, you create the input output pairs. Now, the input pair is created by taking this entire completion sequence except the last token, which means we do not take the full stop here. And the output is created by all the tokens except the first tokens. So you can remember it in your mind as input is something like all but last, and target is something like all but first. And if you arrange input output like that, you can clearly see that these are the input output pairs. For where is the output. For is Pune is the output. For Pune question mark is the output. And you can see they are matching. The inputs are there are 8 input tokens and there are 8 output tokens. This is exactly how the input output pairs are created using just this single line. And then you create the training pairs, which is easy to understand from this visualization, that where maps to is maps to Pune, Pune maps to question mark, etc. Okay, so whenever in any piece of code you look at these lines, it should immediately hit you that you are looking at all tokens except the last token, and here you are looking at all tokens except the first token. And this is a line of code which is used to create input output pairs. That should immediately hit you. And then after you do that, the next step is calculating the log probabilities. Now this is where it gets very interesting, and I want to help you understand this. This also happens using one single line of code. But the first step here is to create these input output pairs. Okay. Now we have to calculate the log probabilities, which is this expression log pi AT given ST, which is log pi A0 given S0, log pi A1 given S1, log pi A2 given S2, etc. So how we are going to do that is, first let us look at the transformer architecture. First the token passes through the token embedding, then it goes through the position embedding, then it goes through the transformer layer where it goes through the multi-head attention, the addition and the normalization layer, feed forward network, and then another normalization layer. And then this was the projection layer I was talking about, which is not there for the reward model, where you can see it is projected to the vocabulary size. And when you project it to the vocabulary size, you get these numbers which are called as logits. And you apply a softmax and you convert these numbers into probability values like these. So it will become clear once we take an example in this next step. Okay, so now this is the LLM architecture. The token passes through the input block, transformer block, output block, and then finally you get these raw logits. Okay, so let's look at the raw logits again. For example, if you pass the token where, you get 50,000 raw logits. Okay, and then you have to select the raw logit which is corresponding to your action. For example, for this state where I have taken the action is, so I will only look at this 8.5 value. For the state is, I have taken the action Pune, so I'll only look at this 9.1 value. For the state Pune, I have taken the action question mark, so I'll only look at the 7.8 value. So out of all the 50,000 values, I'll only look at the action which I have taken. Okay, now we are almost there. After this, all we do is we calculate the soft max and convert that to a probability value. That's it. So this is how we get the log probabilities for all the tokens in the sequence. Okay. Now, uh, okay, but what is the line of code to do this? There is just one single line which is used to do this, which is model.log probs completion minus comma target, which are the input output pairs. So in the explanation, I explained to you a lot of things, right? I explained to you how the token goes to the output, then it projects into all the vocabulary space, and then I only select the logic corresponding to the action that is mentioned in this target. This target is explaining which action should you extract from all the projected uh, actions in the vocabulary space. Okay, so to calculate the log probabilities, only three lines of code are sufficient. And that is exactly what how we can calculate this log pi at given st. So one major part of the expression is already calculated, it's done. And if some of you are not very comfortable with this, I would really encourage you to understand this transformer architecture, which is very interesting, and it keeps on coming in a lot of these explanations. For example, in the reward model, I utilized it, and then even right now, I utilized it. And the same explanations or concepts keep on coming in all these explanations, like the input block, transformer block, output block. And I'm using the word projection a lot. So that simply means that you're projecting from the hidden layer to the vocabulary layer. So once you revise this, you will be able to understand this much more clearly. Okay, so this is how the log probabilities are calculated. And next we have another term here which is called as the advantages. And I am going to explain to you exactly how these advantages are calculated, but I am going to do that taking one practical example after some time. So for now, you just need to know that these advantages are very closely linked to the rewards. And how are these rewards calculated? So as I said before, we get only one single reward at the end of one completion, but that is not completely true. There is a concept called reward hacking. Reward hacking means that our reward model is, if our reward model is trained to give, let's say, positive rewards to happy sentiments, then our LLM might just hack the rewards by saying things like love, love, happy, happy, good, good, something like that. So it has no contextual meaning, but you get high reward because you're using all the right words. So to prevent this from happening, people use a metric uh, which quantifies how different is the current model from a reference model, and that is quantified by taking the KL divergence of the tokens which are predicted by the current model and the tokens which are predicted by the reference model. So this is done by taking the KL divergence, and there is a simple formula for this KL divergence where we can simply subtract the log probabilities of the model which we are training and the model which is the reference model. It is like this. So here it's a bit horizontal, so you might have to rotate your head a little bit. But this is our model on the right which we are training, and we get the log probabilities here. This is the model which is the reference model. We get the log probabilities, and then just we take the difference of them to calculate the KL divergence. Okay, so that is done for all the tokens in the sequence, but the reward is only obtained towards the end. So this is how the rewards are constructed. The rewards are basically for all the tokens, it is just the KL divergence. But for the last token in the sequence, you assign a token which is the reward. Uh, for the last token in the sequence, you assign the reward predicted by the reward model. So this is how the rewards are given for a specific sentence. For example, if I take the example where is Pune? Pune is in India. So all of these tokens, where is Pune, etc. All of these will get individual reward values based on their KL divergence comparison with the reference model. But the last token, which is the end of the text token, that will get a reward which is for the entire sentence, which will be given by the reward model itself. So we are going to look at a very visual representation of that here in the reward model training. But for now, I want to move ahead because that I have planned in the next half of today's lecture. Okay, so now in the last lecture, we also saw that using vanilla policy gradient, which means that we do not use the advantage function at all. Instead of the advantage function, we just use the reward, which is also called as reinforce method. Now, using that simple method, we can actually fine tune the GPT-2 micro model to align the output to generate positive stories. And this actually works really well. It's a pretty small model, 1 million parameters, but we do the pre-training step, we do supervised fine tuning, and then we also fine tune the model using reinforcement learning, but using vanilla policy gradient method, which means that we do not use the advantage multiplied by the log probabilities of the actions, but we multiply it simply by the reward. So that is what I explained in the last lecture, how exactly that works. Now, in today's lecture, what we are going to do is that we are going to understand another policy gradient algorithm, which is very, very common in modern RLHF implementations, which is called as proximal policy optimization, or PPO. And it is actually very simple to understand. Once we have understood the vanilla policy gradient methods, we can easily understand this modern algorithm. But to understand that properly, we need to first understand the concept of importance sampling. So, importance sampling is a concept which appears in probability in a number of different disciplines, and the concept is really powerful. So, let's take an example. Let's say we have an element X, okay, or a sample X for which the probability distribution is P of X. And now, let's say we want to calculate the expectation of a function of this sample, which is f of x. So the formula for the expectation states that you multiply the probability of the sample times f of x, and then you sum it up over uh, all the possible instances of that sample. So this is a formula which is used to calculate the expectation of a function, which is given by the summation of probabilities multiplied by the function itself. So this is something where if you're finding this difficult to understand, imagine f of x to be just simple x itself. So then this becomes summation of p of x into x, which means that we are looking at one instant of the sample. We are looking at the probability of that instance, and then we are summing it up over all the possible instances of that sample. For example, if you are rolling a dice, what are the different instances? You can get either 1, 2, 3, 4, 5, 6. Now, what is the expected value? You take one instance 1, you multiply that with the probability of that instance, which is 1 by 6. So 1 into 1 by 6 plus 2 into 1 by 6 dot dot dot, you can calculate the expectation of x. Similarly, but we replace x by f of x. Now, what happens in importance sampling is that, let's say it is difficult to sample from X. For some reason, it's not possible for you to collect these different instances. So if you ask me the question that, Rajat, it's very difficult for me to sample from X, how can I calculate the expectation of f of X? So an answer which I can uh, give you is that, okay, it's difficult to sample from X, but is there any distribution from which you can sample from? So let's say you say yes, there is a distribution which is called as Q. So then I tell you that, okay, fine, you sample from Q, no problem, but you just have to make a modification to this expression where you have to multiply f of x not by p of x, but by p of x divided by q of x, which is mentioned over here. So the formula remains exactly the same, but since we are sampling from q, we have to divide it by q of x. Now, this is exactly what happens in the importance sampling technique, where people, if there is a better distribution where we can sample from, we go ahead and do that, but we modify the formula for the expectation. So we can actually understand this by taking a very nice example. So let's say there are two samples, okay, P of x and Q of x. And I want to calculate the expectation of P of x, which is shown in red. Now, visually, I can see that this expectation is somewhere around 3, right? Which is where the mean appears to be around 3. But it's very difficult to sample from Q. So what I do is I sample from Q instead. But now if you just sample from Q, you will get a mean which is 6, which is not correct. So what you do is you sample from Q, but you multiply each sample by P of x divided by Q of x. Now that will ensure your mean is also divided by the mean of P of x by the mean of Q of x. So the mean, which is 6, that is multiplied by mean of P of x divided by mean of Q of x. So then the mean also matches. This is exactly what happens in importance sampling. We sample from another distribution, but we make the adjustment by multiplying it by the appropriate ratio. Okay, so this is the only probability concept that we need to understand before we move ahead to proximal policy optimization. Now let's go ahead. Now what happens is that why am I discussing this now? The reason I am discussing this now is that what happens when you train a model using RLHF is you are collecting samples, you are collecting trajectories, and then you are optimizing the model. You are again collecting trajectories, you are optimizing the model. So that is not very efficient. And the reason is it's not very efficient is that let's imagine a model which undergoes one round of training. So now we have to wait for that round of training to be completed. Then we have to sample again from that newly trained model. Again, wait for the round of training to be completed. Again, sample from that newly trained model. So the question is that can we eliminate this sampling step again and again, which is happening in all the iterations of the training? Because that will save us a lot of computational time and cost as well. So then what people said is that instead of this form of online sampling, where you are sampling from the policy which is continuously changing, you sample from an offline policy, which is a policy which is trained up to some extent, but you sample from that and you use that, you use those values of the trajectories in your gradient ascent formula. So this is something which has proven to be extremely efficient while computationally implementing uh, these algorithms, these reinforcement learning algorithms for large language models, because sampling is something which takes time. Uh, Sampling requires querying the model and generating a response. So that is very time consuming because you need to do a lot of matrix multiplications, etc. So instead of that, you sample something offline, keep it there, and then use those values for training. But to do that, we need to make one small change. So this is the original model, right? But now we want to sample from this model, which we are calling as pi offline or pi old. But from the previous discussion on importance sampling, now you know that to sample from this, we can definitely do that, but we need to multiply the relevant expression by P of x by Q of x, which is pi theta divided by pi offline. So this is the original expression. And now this expression becomes this same original expression, but there is one additional term which is added, which is P of x by Q of x, right next to the gradient here. So this is how the original expression changes, but it allows us to sample the states and actions from an old policy, and actually advantages are also sampled from that old policy. So all this data, all this trajectory related data is sampled from an old policy, and then that is multiplied by this factor. So you can actually visualize this very nicely through this diagram. So the first step is that you have an offline policy, which is, let's say, some version of your LLM. And then you sample trajectories from this offline policy. You calculate the sequence of states and actions, and you calculate the rewards and advantages for all of these state action pairs. And then you take a mini batch of these trajectories. Remember, all these calculations are already performed before I start the training. And then you start the training. You run the gradient descent to train the online policy. Now, in this expression, some of you might be questioning that uh, is everything done offline or is something done online also? So something is definitely done online, because you can see here there is this pi online 80 given ST. So some portion of this is definitely online, but a majority of uh, the state's actions and the advantages, all of these are calculated in an offline manner. So now we are fully ready to understand the proximal policy optimization. We have just made a small tweak to our gradient ascent formula, which has come from the policy gradient theorem and our discussion related to policy gradient, where we have the same terms, grad of log pi, and then we have the advantage also. The only difference is that we have multiplied this by one additional term now, which is pi online divided by pi offline. And this is going to give us a lot of advantages with respect to performance. Now, for vanilla policy gradient methods, we know that the gradient of the performance measure is given by this expectation over all the possible trajectories, and the expectation is calculated by taking the product of the gradient of log probabilities of the actions and the advantage. Now, this can be written as an objective function whose gradient we are calculating. So this gradient can be obtained by taking a gradient of this expression. There is just a delta sign which is missing from this and this. So essentially we can say that in vanilla policy gradient method, we are trying to maximize this objective function. So basically the curve, this is the curve and this is L of theta, and we are trying to reach the maximum of this. And to reach the maximum, we need to find the gradients, right? At every step of the way, we are taking a step in the gradient direction, and that is given by this expression. Now, if we use importance sampling, this objective function is modified by one small change where we divide pi by pi old. So we are still maximizing the expectation, but you can see this log is somehow absorbed, and I will come to that how that log vanishes. But essentially, uh, in vanilla policy gradient, we are maximizing this, and using importance sampling, our objective function changes to this. So now why this is valid, you can easily show that the gradient of this is equal to the gradient of the performance measure which we looked at before. So basically, if you take the gradient of this expression, you can see that the gradient exactly matches this. And you can actually prove this also by taking some time, but right now it will take some time to prove it. But essentially, it's very simple. If you take the gradient of this log, you can see that this 1 by pi theta comes outside, pi theta cancels, and then you start to get expression which looks very similar to this. So if you multiply this, if you take this grad, you get 1 by pi theta, and then this pi theta and this pi theta cancels, and you get an expression which looks exactly like this. So in the PPO discussion, we are henceforth going to look at this objective function that we want to maximize.
And it looks very simple, right? It's an expectation of the new policy divided by the old policy multiplied by the advantage function. So we want to maximize this objective function now. Now, the question is that how do we maximize this objective function? And this is where the main PPO magic comes into picture. Please pay very close attention to this discussion now. The first thing that we do is that we define this ratio as R of t, RT of theta. And then the objective function becomes this. We want to maximize the expectation of RT of theta multiplied by the advantage. Okay. Now, how do we maximize this expression? But before we look at the maximization, uh, PPO makes a small tweak to this objective function, and it's a very small tweak, but the main idea comes from this R of t. What does it mean intuitively? It is measuring how much your new policy is deviating from your old policy, right? So, in the PPO paper, the authors argued that why don't we clip this ratio? So we don't want the new policy to deviate too much from the old policy, and we don't want to make any aggressive updates to my policy. That is the only intuition which is there in PPO, through which the formula comes later, which we are going to see. But once we arrive at the formula, you might forget the intuition that we started out with, which is we don't want the policy to deviate so much from the old policy. And that is the idea which must have come to their mind in 2017 when this paper came out. And then they thought, okay, fine. If if R of theta is measuring how far does the new policy deviate from the old policy, can we just clip R of t if it reaches a certain value? And that is exactly what they did. Can we achieve this simply by clipping R of t if it moves too far from the value of 1? And look at this curve, that is exactly what they did. So on the x-axis we have R of t, and on the y-axis we have clipped of R of t. So if the value is less than 1 plus epsilon, uh, you say fine, no problem. But if R of t starts to increase, then you basically clip it. And this is only done for advantage which is greater than 0. Now, what does this mean? If advantage is greater than 0, it means that your action is better than the policy's default behavior, which means that your policy is moving in the right direction. And if you are moving in the right direction and if this ratio becomes very high, it means that you are going to end up making aggressive updates. So PPO is all about not making aggressive updates. We do not want the new policy to deviate too much from the old policy, and it clips it. Okay, so this clipping is only done for advantage which is greater than 0. So now this can also be written as minimum of RT of theta comma 1 plus epsilon. So if it becomes greater than 1 plus epsilon, then it just clips it to 1 plus epsilon. Now the question is, what happens if the advantage becomes negative? And this is where it's slightly subtle in this discussion. So if the advantage is negative, this means that the selected action is performing poorly than the policy's default behavior. So even if RT values become very high, I am okay with it. And the reason I am okay with it is because the advantage is negative. Even if my new policy is uh, very different from my old policy, but because the advantage is negative, it's not going to make drastic changes to my policy. On the other hand, if the policy is if the action performs poorly than the policy's default behavior, and if let's say R of t values is very close to 0, then I am worried that I am not penalizing my action that much. So the penalization is actually done for lower values of R for negative advantage as opposed to higher values of R. So let me just repeat that again. Let's say if RT value is very high, it's more than 1, it means that you are already penalizing your output because the advantage is negative. So you are not focusing on that action, you are reducing the probability of taking that action when you encounter that state. So you are not worried if RT becomes very high. But if RT value is around, let's say, 0.2, then you are worried that, okay, if RT is 0.2, uh, does it mean that it's not going to penalize my action that much? So I want the policy to penalize the action even for ratios which are very small. So essentially, for advantage negative, the we are becoming slightly more aggressive in saying that no, even if RT is very low, I want it to penalize slightly higher level. So the way you can represent that in terms of this graph is like this. For higher values of RT, you just don't make any change, you just continue it. But let's say if RT is very small, imagine this region, if I did not do any clipping, it would mean that I am not penalizing my action that much. That's why you clip it, so that you penalize it more. So it is a different logic as compared to advantage greater than 0. And it might take some time for you after the lecture to think about it and understand. But when you do, you realize that it makes sense. So essentially, the clipped up function can be written as maximize of RT of theta comma 1 minus epsilon. So don't focus too much on these functional representations, but essentially you can see that we have two graphs, right? We have this graph for advantage positive and we have this graph for advantage negative. That is all you need to know about PPO. I am going to do one mathematical simplification now, which is going to make the expression look very good and very compact. But for an understanding perspective, if you understand this much, it means you have understood the core objectives of proximal policy optimization. Now, just to mathematically simplify it, combining the two graphs, we get something like this. So, for advantage greater than 0, you have the red graph like this. And for advantage less than 0, you have the blue graph. Okay, so we want either one of the following. So let's look at this again. For values of r between 1 minus epsilon and 1 plus epsilon, there is no problem because it's the same for positive advantage or negative advantage. But if advantage is greater than 0, then we have this. And if advantage is less than 0, then we have this in this segment. So now let us call this f, and this is simply r of t. So because we want either one of this, we can write this as a very compact expression as we want minimum of f comma r of t into sine of the advantage. So let us understand what is happening. So first of all, let's take the case of advantage is greater than 0. Okay. If advantage is greater than 0 and if you are operating within this region between 0 and 1 minus epsilon, then let's see which is the minimum. This red is higher than this blue, right? So this is the minimum. So this portion will be selected. However, if advantage is negative, then this portion will be selected. Similarly, for this range, for 1 plus epsilon to infinity, if the sign of advantage is positive, then the minima is this, which is what we want. But if the sign of the advantage is negative, then this will be selected. So this formula is a very nice representation for us to, in one single compact expression, we can represent what we want. And now the objective function becomes expectation of minimum of this f is, I'm just writing it as f rt of theta into advantage comma f into advantage. And this f, this is written as the clip function. So this is written as clip of RT, comma 1 minus epsilon, comma 1 plus epsilon. So the final formula, it looks something like this. We are minimizing two terms. The first term is RT into advantage, and the second term is this clip function into the advantage, which is exactly what we have written here actually. But the only difference is that we are replacing this f with the clip function, and then we are multiplying one more advantage at the end of it. Okay, so now the main intuition for the model not deviating too far from the old model is that when you come to the reinforcement learning stage in the RLHF pipeline, you have a step of supervised fine tuning before that, right? And in the step of supervised fine tuning, you have already achieved a model which performs okay-ish. So you don't want the model to make very large changes to the weights. That is exactly why PPO works, and it has proven to be extremely effective for RLHF tasks. You can see that it's very similar to vanilla policy gradient. The only difference is that we are looking at the value of R of t and then basically clipping it depending on the positive or negative values of the advantages. And then this objective function we are denoting as L clip of theta. Now the gradient ascent becomes simple, theta t plus 1 equal to theta t plus alpha times gradient of this objective function. Okay, so now in proximal policy optimization, this is just one objective function, and in the paper which they outlined, uh, there are totally three objective functions. And one of the objective function you might recall from our discussion last lecture is that of value function. So remember that to calculate the advantage, we need an estimate of the value function, and the value function itself is a model. So this is another loss that we want to minimize, which is the value function predicted and the target value function. Okay, so finally we want to maximize this L clip we want to maximize, and this, because this loss we want to minimize, there is a negative sign associated with it. Essentially what this is meaning is that we want to not just maximize our objective function for the PPO, but we also want our value function prediction to be as close to our target value function. And then there is one last term which is added to the objective function, which is called as the entropy. So the entropy of the policy is given by this expression minus summation of pi of theta into log pi of theta. And then the goal is to favor policies which maximize the entropy. And the intuition of this comes from the exploration and exploitation dilemma in the reinforcement learning, where maximizing the entropy ensures that you are exploring more actions. Your LLM is exploring uh, more action tokens as an output. So the final objective functions becomes we want to maximize this. This L clip is the loss from or the objective function for the uh, proximal policy optimizer, where we want to not allow the model to deviate too far from the original model. This loss comes from our attempt to match our value function as close as possible to the target value function. And this is an entropy which we want to maximize. Now, when I came across this formula, I was not very satisfied because I was not able to visualize this value function properly. And I did not visualize, I mean, I could not visualize the entire PPO process. There are so many components, right? In your mind, you might be wondering that, okay, fine, log probabilities, we looked at the visualization, but now you have to calculate the advantage also. And for the advantage, you want to calculate the value function, and then you want to optimize the value function also. So there are multiple components which are uh, happening parallelly. And my first objective in this lecture was to help you understand the theory. Once you understand what is PPO, in your mind it won't be a very complicated algorithm, but it has a very simple intuition behind it. And then we are also going to look at a nice visualization where we will look at the entire PPO training loop very properly. So all the doubts that you might be having with respect to the tokens, how exactly each token maps to each component, it will become clear as we move ahead. Now, what we are going to do is that we are going to take one interesting example, which is one of the first examples OpenAI considered when they wanted to test whether the PPO algorithm works in practice or not. And this problem statement is called as text summarization using RLHF. Basically, what we are doing is that we want to summarize Reddit posts, and we don't want to just summarize it based on some data, but we want to include human preferences also. Okay, so we are going to look at how to use PPO based reinforcement learning training to summarize Reddit posts according to human preferences. And once we look at all the modules, we are going to understand this entire code and what's exactly happening in this process very properly. But and then there are overall two main components. One is reward modeling and second is PPO training. We are going to understand both the components in this section. Okay, so now before I go ahead, I want to take one small break for 5 minutes. And then what we will do after the break is we are going to look at the summarize Reddit problem for another hour. We are going to understand all these aspects in detail. And this will be very relevant for you because teaching theory is fine, learning theory is fine, but it's not useful unless you know exactly where that theory is applied in the code which you are writing. So that is exactly what we are going to do in the next part. So we will just take a break for 5 minutes and then we'll continue with part number two. Okay, so before we start approaching any problem in RLHF also, after uh, these lecture series are completed, you might tackle some RLHF problems on your own. Uh, the first step that we should always think of is that what is going to be our reward model? So, how exactly are we going to score the preference data sets? And how exactly are we going to construct the reward model? So, we are going to understand a very step-by-step process of how exactly are these reward models constructed. So, firstly, to construct the reward model, we need a good data set. So, this is the data set which we are going to look at. It was used by OpenAI for this exact same problem. You can see that there is a prompt here. Let's look at one. And there is a chosen response and then there is a rejected response. So this is currently in the relationships category. And then there are a lot of different questions. So for example, let's take this example. How to stop stray cats from invading my garden. I need help, and this is the prompt. There are a lot of things. And then uh, we are asking people to basically summarize this prompt. And there are two ways in which we have summarized. So the first is I have a small garden and stray cats are always coming in and ruining. How can I stop this? Second is I have a friend who has been feeding stray cats. I live in near, would like to report this. Okay, so this is the chosen response. This is the rejected response. So we have three data attributes. We have the prompt, we have the chosen response, and we have the rejected response. If you look closely, you can see that all of these responses have different lengths, right? The prompt is different length, the chosen, rejected, all of these have different lengths. But I really like the format of this data set because this is exactly what we need for constructing our reward model in the first place. Now, before we construct any reward model, the first step that people always do is they uh, they process the data. So how the data is processed is, let us go back to our tool. So in the reward modeling, the first step is the reward model data processing. Okay, so don't worry about all the text which is happening. I'm going to walk you through all of it. So look at this prompt. Okay, there is one prompt, there is a chosen response, and there is a rejected response. So the chosen response is summarize, or the prompt is summarize the following article in one sentence. Pune is a vibrant city in India known for education and culture. The chosen response is Pune is a major Indian city celebrated for its education and culture. And the rejected response is Pune is somewhere, I don't know much about it, maybe a place with something happening. Okay. Now I have selected a block size of 32 here, which means that uh, the final prompt plus the final completion will have a size of 32 tokens. Now, firstly, this prompt can be broken down into 22 tokens. I have taken the liberty of assuming that each word corresponds to a single token here. And the chosen response corresponds to 13 tokens. The rejected corresponds to 20 tokens. So the positive sample, which is also called as the positive completion, it has 35 tokens, and the negative sample has 20 plus 22, that is 42 tokens overall. So naturally, you can see that these number of tokens is higher than the block size. So what we do is, this is the original positive sample, which has 35 tokens. And you can see here we have removed the first three. We directly start from 2633. We don't take these first three tokens. Similarly, here we remove all the tokens up until this point. All these tokens are removed because we want to match the block size. The important thing is here is that we are only truncating the first part. We are not truncating. We are not starting the truncation from the last. And there is a very important reason for it. If you are giving reward to the entire completion, the major chunk of the context lies in the answer, right? Not in the prompt. So that's why you start the truncation not from the answer, but from the starting of the prompt. Now the question is that what happens if I have a higher block size, let's say 65. Now you can, or let's say 50, or yeah, let's take an example of 50. So now you can see that the number of completion tokens in the positive sample and negative samples are less than the block size. In that case, what people do is that people pad this with a end of text token, which is 50256 in this case. So this is called as padding. Whenever you look at LLM related codes, you might see this padding word used multiple times, and initially it used to confuse me also. But essentially, why padding is done is because we want to make sure that all the samples they are of the same size. For example, here you can see if I add prompt plus chosen, all of them will have different sizes. And if I have a fixed block size, I can just pad them so that all of them become the same size. So that is usually useful for processing when we are passing all of these samples together as a batch. It usually helps if all the elements in this batch have the same size. Okay, and now what we do is if you pass this entire sample to the model, uh, you are not passing the entire information because all of these padded tokens, they don't make any sense, they don't have any meaning. So you have to tell the model that look, these are the tokens which I don't want to care about, so you can neglect these tokens completely. And that is done by applying something called as a mask on these uh, this entire completed sequence. So the mask tells that all these green tokens are active tokens, and all these white tokens are non-active tokens. So along with the completion, I also pass a mask. Along with the positive sample, I pass a mask. Along with the negative sample, I pass a mask. And that is exactly what is done as an input. Okay, so whenever you are processing this data, you first have to make sure that there is a padding done to make sure that all the completions are of the same size. And when you do the padding, you have to apply a mask also because not all the tokens are important. Okay, so that is the first step, which is the reward model data processing to make sure that the uh, completions, both positive and negative, are of the same size, and we are telling the model which tokens to look at. Now, what we do afterwards is we build our reward model. Now, this is a very interesting uh, way in which it is built. We have already looked at the formulation of the reward model, but let's understand. Okay, so as we have seen in the last step, we pass the prompt plus the chosen, which is the positive completion, along with the positive mask, which is the completion for the which is the mask for the positive completion, and we also pass the mask for the negative completion, or the rejected completion. Now, after we do that, uh, what we do is we pass this to the reward model, and the training will start. Now, before I start the training, I want to explain these different numbers to you. So R rejected is the reward which the model gives for a combination of the uh, prompt plus the rejected answer, and R chosen is the reward which the model gives for a combination of the prompt plus the chosen answer. Okay, and the difference is between the chosen reward and the rejected reward. So we want this difference to be as high as possible. So as the training starts, this might be negative, but it might slowly move on to the positive category. And as we saw, the loss is given by minus log of sigma times delta. So this log we want to decrease. Now, what are we training here? At the end, there is a linear head, which is from the output of the transformer block to a single scalar value, which is the reward value, which is predicted by our model. Now, once we start our training, you can see that the delta grows, which means that we are doing better and better. Our model is widening the gap between the chosen response and the negative and the rejected response. And then you can see that the loss is also decreasing, which is kind of makes sense. If delta increases, loss will decrease. That is how we have constructed the loss function in the first place, which is exactly what we want. And these are the weights which are updated in the final layer, which is the linear layer, which projects from the transformer layer to a single scalar value. Uh, I do not have a visualization included here for that, but I have a very nice visualization for the value model, and that is very similar to the reward model. So you can understand that through the value model itself. For now, just remember that there is a final layer which is added to the LLM architecture by removing the projected layer, and we get one single value. So this is how the reward model training happens. And slowly we are going to replicate a piece of code, and we are going to see how exactly all of these pieces of code are used in that project where we want to summarize the data. Okay, so now this is how the reward model is constructed and how the reward model actually works, how the reward model is trained. Before we start the PPO step, the reward model has to be trained and frozen. We do not train the reward model again when we do the PPO training. Now, very similar to reward model, we have something called as the value model. And if you understand this value model properly, you understand the reward model also properly. So please pay close attention because this is very visual. Okay, so this is a complete token journey. We are going to understand this journey step by step. The first step is the token embedding. So I'm passing the token where, and then I embed it into 768 dimensions, which is also called as the hidden dimension. So in the last lecture, we had used an analogy of a uniform. So this is something like a personality chart where every single dimension tells something more about the token. So this is the token embedding process. After the token embedding, you pass this through a transformer where you pass it through the attention block and you pass it through the feed forward network. But the dimensions are preserved. You can see the final dimensions are also same as the initial dimensions, which is 768. Now, okay, so this is the input block and the transformer block. Now the very important step for us is the last step, which is the in while predicting the value, we do not have the projection layer here at all. The transformer output is connected to one single value, which is the value of that particular token. So there is a single matrix which takes these 768 values and outputs a single scalar value, which is the value of that particular token, or in RL language, it is the value function of that state. Now, this is the exact same architecture for the reward model also. The only difference is that the reward model is calculated only towards the end of the token and or towards for the last token in the sequence, but the value is calculated for all the single tokens in the sequence. So this is how the overall process works. You pass the token through the embedding, then you pass it through the transformer block, then you pass it through the value head, and finally you predict the value. So that is why I said initially that the reward model and the value model are very similar to the LLM architecture. The only difference is that there is one value head here. In the case of reward, there is a reward head, and that's how you get one single value here. So this is one visualization I want you to keep in mind, because in the PPO step, we are going to use this value from the value model. And now you know exactly from where this value we are taking. Now, one important difference between the reward model and the value model is that the reward model is frozen. We are not changing the weights of the reward model in the PPO training step, but the value model is not frozen. We are changing the weights of the value model as we proceed with the PPO training. Okay, so now once we have understood how the reward model is created, how the value model is constructed, we can now move on to an important section, which is how do we exactly calculate the advantages? And this is something which is slightly involved. So I want you to really pay a close attention, because the advantage calculation is very important. As all of you know, in the gradient of the performance measure formula, we have already looked at how to calculate the log probabilities, but we haven't really looked at how to calculate the advantage. And the advantage is going to rely upon the rewards collected from the reward model and the values collected from the value model. So let's understand how to calculate the advantages for all the tokens. Okay, so now the first thing that we are going to look at is, for this understanding, we are going to take one example which has where is Pune question mark. Pune is in India full stop. So overall there are 9 tokens here in this. Okay. So our final objective is to calculate the advantages for all these 9 tokens. So just keep that in mind. Now, the first step that we do to calculate the advantages, we calculate the log probabilities for all of these tokens. So for example, the log probabilities of where for the original model, so the original is the model which we are training, and the reference model. So this reference model is fixed and frozen like the reward model. It is not continuously updated. This is usually the model which we get after the supervised fine tuning step. Okay, so we calculate the log probabilities. Now, how these log probabilities are calculated, we looked at in one of the modules. It's straightforward to calculate these log probabilities in one single line, which you can see here, exactly how it is done for the original, for the model which you are training and the reference model. And we simply take a difference between these to calculate the KL divergence. So we get the KL divergence for all of these tokens, which is where is Pune question mark. Pune is in India. And all of these tokens, we find the KL divergence. So that is the first step. Now, why is this KL divergence calculated? Remember in our discussion for reward hacking, we do not want the model to deviate too much from the previous model or the reference model after the supervised fine tuning step. So this scale model is considered to be like a reward for all these tokens. Uh, so if, but with a negative sign. So for example, if the KL value is very high, then the reward should be negative of that, because we want to penalize tokens which deviate too much from the reference tokens. So we do not want the scale values to be high. We want them to be as low as possible. So that is the first step. We calculate the KL by taking the difference of the original log probabilities and the reference log probabilities. If anyone is interested where this KL divergence formula comes from, there are actually 3 ways of representing the KL divergence, and what we are looking at is one of the most popular ways. but GRPO algorithm which DeepSeek used, they used a different representation for the KL divergence. But for now, this is good enough for our understanding because this is exactly what is used in PPO calculations. Okay, great. Well, now we have obtained the KL divergence for all the tokens. Now what we do is the KL divergence is obtained for all the tokens, but we have to calculate the scores, which are the actual rewards. Now, to calculate the scores for all of these tokens, the KL divergence is calculated, but we are getting one final reward for this entire sequence using a reward model, right? Because this is the prompt and this is the answer. So this completion we pass to the reward model and we get a final score, and that is appended in the end. Okay, so what we do is, firstly, for all of these tokens, we multiply this with a negative sign because we want to penalize higher values of KL divergence, and we multiply that with beta. And then we attach or append one single reward to the end, which is associated with that entire sentence. Okay, so all these tokens get single value, and there is one final reward which is attached towards the end. So this is the combined score vector, which typically has a length of the sequence plus one, because you are appending one reward at the end. So you can consider this to be your reward vector itself, where this is the reward which is given for the end of text token. So this is how the entire score vector is constructed. So now in your mind, whenever you see any trajectory or a sequence, you should know that even though the reward comes only for the last end of text token, for all the other words, we are calculating their own rewards by taking the KL divergence, taking the negative sign of that and multiplying that with beta. Okay, so this is something which you should visualize in your minds after this module. Now, we have the KL divergence, that is great. Now we can also get the value predictions for all of these tokens, right? And how do we get these value predictions? We already have the value model which is being trained in the process, but we can use that value model and we can get the values for all of these tokens. And it will be a single value because we saw that the value model predicts one single scalar at the end. So for where we get a value, for is we get a value, for India we get a value. And then we also append one last value which is written 2 here, but usually this is 0. So in the code that we are going to look at, this last value is 0. And why is this last value added? Because the length of the score vector should ideally match the length of the value vector. Okay, so we calculate the scores, we calculate the values. Now we are in a very good position to calculate the advantages. If you remember the advantage formula from our last discussion, but anyways, if you don't remember it, I'm going to explain the process. So to calculate the advantage, you start from backwards. So now this animation will start from step t equal to 8, which is the last token in the sequence. Okay, so for this last token, you calculate the advantage, then you move back to the second last token, you calculate the advantage, again move back, and then in a similar way you can calculate the advantages for all the different tokens in the sequence. Now I'm not going into specifics of how it is calculated, the mathematics, but it is not very difficult to understand this. This is using the generalized advantage estimation, which we have covered in the last two lectures. Okay, now these advantages, you can see they are calculated for all the tokens. Now there is one interesting thing you might see, which is called as the return. Now what is this return? Uh, Remember the formula for the advantage is Q minus V. So now if you do Q minus V and you add V, finally you get Q, right? This is exactly what the return is. And I'm going to tell you why this return is calculated. We could have just calculated the advantages, but we calculate the returns because let's go back to our theory. So when we discussed PPO, we discussed that we want to minimize the loss between our value model and the target. Okay, where is that? Uh, yeah, this is the loss function that we want to minimize. But one question might have appeared to your mind, how do we calculate the target for these values? Now, this target is exactly the same as this return. These returns are used as targets for the values because the definition of the value is expectation of uh, expected return from that state till the end of the episode. And if you add the advantage to the values, you will get something which is called as the action value function, which also means the exact same thing. So that becomes the target for your value function. That is why we need both the advantages and the returns after this step. So now in your mind, it should be clear that, okay, fine. When I get a sequence, what do I do? First, I calculate the log probabilities for all the tokens for the model which we are training and the reference model. Then we subtract them. We calculate KL divergence for all the tokens. Then what we do is we calculate the rewards for all the tokens by multiplying the KL divergence by beta and a negative sign. And then we append that by a single value at the end, which is the reward value that we get at for the entire sequence. Uh, so this is how the score vector is calculated. Next, we can use this score vector and then, okay, then we keep this score vector aside. Then as a next step, we calculate the values for all the tokens in the sequence. For the end of the text token, we assign a value of 0, but for all the other tokens in the sequence, the values can be calculated by using the value model, where we have removed the projection layer and attached one single layer where we get a single value. So now we have the score vector and the values. Now we are all set to calculate the advantage for all the different tokens, and the advantage calculation proceeds from the end, from the last token to the first token. And we can not only calculate the advantage, but we can add the advantage to the value from the value model to get the returns. And if you are confused how this calculation is done, this directly comes from the generalized advantage estimation, which is just a recursive formula in which you calculate the advantages for all the tokens. So now we have properly understood how the different aspects of our code are working. And at this step, I want you to I want to take you through this some part of the code which I'll be showing to you right now. Uh, so go to this GitHub repo, and in this GitHub repo, uh, you can go to RLHF part 1 folder, and within that you can go to summarize RLHF. And within summarize RLHF, you have to run three files. One is summarize supervised fine tuning, summarize reward model, and summarize GPT. For now, click on this supervised reward model. Okay, so now in this code, there are a lot of things happening, but I want to explain you exactly what is happening. So if you scroll down, you can see that this is where we are doing the padding and the masking, which is what we mentioned in the data processing step. And this is how we are constructing the uh, prompt plus the mask. So this is the chosen answer and the mask, the rejected answer and the mask. And then at the bottom, you can see the training loop for the reward model, where this is the training loop, and this is passed to a reward model which is defined somewhere else. I'll explain that, but essentially this is where you're training the reward model to reduce the loss. And along with this, you're passing the positive samples, uh, the negative samples, the mask for the negative samples, the positive samples, and the mask for the positive samples. Then you're doing a backward propagation and you're optimizing it. So this is a standard training loop which you are running for training your reward model. Now, one of the things that you will see towards the end is there is a line which says model.load dictionary. Now, this is a very important step. What happens is that to train the reward model, you don't start from scratch, but you used the weights obtained from the supervised fine tuning step, and you use the exact same weights for the reward model in the input layer and the transformer layer, because the last layer anyways is a different, it's a linear layer, not the output layer. But the input layer weights and the transformer layer weights are exactly matched with these weights from the supervised fine tuning model. And why this is done is because it allows us to train the reward model in a much faster way. Since we have a previous checkpoint from the supervised fine-tuned model, we use that same checkpoint. Okay, so these are the main pieces of code through which you will be well equipped to understand this entire code. Let me again explain it again. This is where the prompts are, the prompts and the chosen answers, rejected answers are collected from this data set. This is where you do the padding and the masking, and this is where you generate uh, the chosen completions, the chosen mask, the mask for the chosen completions, the rejected completions, and the mask for the rejected completions. And then this is a training loop where you pass the chosen rejected sequences along with their masks. And we are going to look at what this model is. And then finally, here, before we start the training, we do this where we load the weights from the supervised fine-tuned model inside our reward model, which we are trying to train. Now the question is that what is the reward model? So you can actually go to this min GPT, and within that you can click on rewards.py. So at the bottom you will see there is a class which says class reward model, and this is where you will actually understand everything that we have been talking so far. So here you can see the transformer block is it remains the same, but we are adding one linear layer, and here we are initializing the weights and the biases of that linear layer. The biases are initialized to be 0, and the weights are initialized to be a Gaussian distribution with 0 mean and deviation of 0.02. So this is something where let me actually show you through this. Yeah, this is exactly what we are doing here, where the transformer block remains the same, but we are adding one linear layer as a projection at the top. Okay, and at the bottom, if you see, our main formula comes here. Uh, Sigmoid of chosen minus log of sigmoid chosen minus rejected, which is what you see over here, minus log of sigmoid of chosen minus rejected, which comes exactly in the same form. And here at the top, you can see there are two things additionally which we are doing. Firstly, when we are passing the input to the transformer, we are passing the token along with the attention mask, because we want it to only focus on the prompt, the tokens which are not padded. We want to not focus on the padded tokens, they don't mean anything. And then finally we get we are predicting the rewards only for the last non-masked value, which means that in this graph or in this figure you can see we are predicting the reward only for the last token, right? We are not predicting the rewards for all of these tokens, but only for the last token. And that is what happens here. We extract the last token in this step, and then we are predicting the rewards only for the last token, which you can see here in these two lines. Okay, so this is how the reward model is constructed. There are three steps. First is the architecture. Second is applying the mask. The third is only extracting the last non-masked value. And the last step is to define the loss function, which is minus log of sigma chosen minus rejected. So you might, to understand the reward model and how it works, you need to only look at two pieces of code. One is under summarize RLHF, go to summarize reward model.py, and then after that you can go to model.py on the in the min GPT folder to understand this entire code. So these two have been explained in these two visualization: reward model data processing and reward model training. Now we want to go to the main part, which is this code summarize gpt.py. And within this code, there are multiple elements which we want to understand properly. So let's start with some things which we can easily understand, right? Okay, so here, have a look at this. We are generating the completions here, and here we are generating the input-output pairs. Like we had looked at in the example, we are generating the original log probabilities by this one single line model.log probs. We are generating the reference log probabilities. Okay, and then values we are calculating from the value model. I will show you how the value model is constructed. And after that, what we are doing is the KL divergence is calculated from the original model minus the reference model. Let me actually show you where we had covered this. So here, the KL divergence is calculated original log prob minus reference log prob for all the tokens in the sequence, which happens here. Then what we do is we calculate a score vector by appending this to the single reward which has been obtained. Okay, so this reward might be written somewhere where we get the reward. Yeah, this is the reward from the reward model. And then this appending is something which I explained here at the end. Uh, yeah, at the end you can see this reward is appended to these KL divergence values. Okay, and then what you do is you pass these to this function which is calculate advantage and returns. But before that, let's look at how our value model is defined. Uh, Value model, as all of you might remember from our discussion, value model is simply this. You have a value head, rest of the layers remain exactly the same. So go to this model.py again where we saw our reward model, and with just above that you will see the value model also. Sorry, rewards.py, not model.py. So here you will see value model, and this is just this line of code. So here you can see the transformer block remains the same. There is a prediction head where it goes from the hidden dimensions to one single scalar dimension, and all the weights are assigned a zero. From they are sampled from a Gaussian distribution with zero mean and standard deviation 0.02, and all the biases are assigned to be zero. And then that is all. You just apply, pass the tokens along with the attention mask, and then you get the value. So this is named as rewards, but you can rename it as values also. So exactly same as the reward model. You can see these lines are same as this. But here we do some more processing because we are only calculating the reward for the last tokens, and we have to take into account positive and negative uh, completions, and we have a separate function for the loss here. Okay, so how is the value loss calculated? I will explain that, but this is how the values predicted by our model are calculated. Now, if you go back to this and where we were discussing about, so we have understood everything up until now, how the rewards are calculated, original log probs, reference log probs, values, scale divergence scores. Now, this is where the advantages are calculated. And this is again in the same file rewards.py, and this is just this function. And what is happening here is we are doing exactly the same thing which has been mentioned here in this step in the GAE advantage calculations. So what we are doing is, first of all, we are passing the rewards and values from our score calculation and the value model, and then we are calculating the advantages and the returns at the end. So this is an iterative step where for each token we calculate the advantage and we go reverse. So this is where you can see it goes reverse from last token to the first token, which is what we saw here. It goes in the reverse direction. So this is exactly how the advantages and returns are calculated. So this is the crux of this entire code. And then after that, there is an important step before we move to the PPO modeling and exactly what happens. What we need to do is that now all of this is uh, not happening while the training is happening. All of this is happening off sample. So it means that it's happening offline. This is what we discussed in our important sampling discussion. All of these advantage calculations, log probabilities, all of these are calculated offline. So far we have not even entered the PPO training loop, but we do all these calculations by generating completions and then calculating all these values. Now, one thing you might have noticed is that we have generated all these log probabilities, we have generated advantages, and we are good to go with in terms of the gradient formula. But all of these might not have the same sizes. For example, some log probabilities, some sequences might be longer compared to other sequences. This is why we need another layer of padding and masking. So let's say we take this example, where is Pune? Pune is in India, and we define a block size of 16. So everything is padded to match that block size. So initially, where is Pune? Pune is in India. It has a length of 9, right? So the advantages has a length of 9, the returns has a length of 9, the log probabilities has a length of 8. And the reason why it's of a shorter length is because the log probabilities are not calculated for the end of text token, which is what we are appending to the score. Uh, so the advantages and returns have one length higher compared to the log probabilities. But all of these now we want to extend to the length of 16. So how do we do that? First thing is we pad advantages and returns. We just pad it with zero values, so that now we have 16 tokens, you can see, in all. But the rest of the tokens, they don't mean anything because their value is zero. Similarly, we pad log probabilities. Again, as they have zero values towards the end, and we pad the token sequences also, the completion tokens and the target tokens. Uh, okay, so this is the padding step, but as we saw in the reward data processing, padding is always accompanied by masking because we need to tell the LLM. So for example, this is the action mask. The action mask not only removes the padding, but it also removes the prompt. Now, this is something very important whenever we are doing or proceeding with the PPO training loop. We are only interested in the complete in the answer given by the model, not the entire completion, which means prompt plus answer. That is why these initial tokens, they get a mask of zero, which means that we want the model to only learn from uh, the output which the LLM is giving, not what the user is asking. That is why this action mask is appearing only at the tokens which are generated. For example, this is where is Pune question mark. Pune is in India dot. All of these tokens are the tokens which are generated by the LLM. So this is exactly what's happening here, where we are doing the padding. So this looks like a lot of code, but if you understand the visualization, that is exactly what we are doing. And why we need to pad it is because we want to pass everything as a batch. And if you are dealing with multiple sequences, you can't pass everything as a batch uh, unless all those sequences in the batch have the same length. So that is very, very important for us. Okay, so now uh, what we are going to do is that we are going to now understand and visualize the entire PPO training loop using this. By the way, if you want to run this, what you have to do is you have to go to this GitHub and go to this RLHF visualizer. And this is a React app, so you can just do npm start. So you'll be able to run this and get this locally on your computer. Okay, so once you do this, there is one last section here, which is the PPO training loop, and this is where everything comes together, which means the reward, values. Now you don't really need the rewards because you have already used it to calculate the advantages. So what comes together is the advantage and the values. So let's understand how the PPO training loop is constructed. So step one in the PPO training loop is the data collection, which means that what are all the prompts that you are going to give to your LLMs to gather your outputs. And this is a very important step, which you can see in this code. Let's look at so there is one popular data set which people use uh, for the prompts. And so if you look at this one, it has a prompt and a label, right? So all of these prompts, we use those prompts to construct the trajectories. So whenever we are training the model, remember that initial step is the offline data collection where we want to generate the advantages, the rewards for all the single tokens, the log probabilities. Now to generate that, we need to construct some prompts, right? We need to construct some prompts, and those prompts are usually related to the uh, the data set or the area which you want to align the model towards. For example, I want to align the model to summarize uh, Reddit posts, right? So it makes sense that in the offline data generation, I give the same prompts which my end user is going to ask, and I'm going to align these prompts so that they get higher rewards. So this is exactly this first step, which is the data collection. You basically give a lot of prompts and then you generate a lot of trajectories and then you generate completions from those prompts and trajectories. And then you have so many sequences, right? But then the question is that how do you analyze so many sequences? But before we get to that, let's look at the next step. Let's say we are looking at one single sequence, right? Which is sequence number 0. Now that sequence is where is Pune? Pune is in India. And we calculate the log probabilities for all of these tokens in the sequence. And not only we calculate the old log probabilities, but later we'll see they are combined with the new log probabilities to calculate the KL divergence. But for now, when you generate a sequence, you can immediately calculate the old log probabilities, because to calculate this, you only need the reference model, which is the output from the supervised fine tuning step. So you can calculate this old log probabilities for all the tokens in the sequence, right? And here I have only written for this because towards the end, we are going to ignore this. Remember the action mask which we talked about? That action mask is applied to the old log probabilities also. So we are not going to look at these prompts, these tokens which are a part of the prompt. So step one, after you collect all the trajectories, is that you can basically calculate the old log probabilities for all the single tokens in the trajectories. And this you can do with a single line of code by creating input output pairs and then using the function model.log probs into bracket completion all but last token, all but first token. So you can easily do this. And then after this, you can immediately you can calculate the generalized advantage estimation. Now the question is, how can you do that? How can you calculate advantage for all these tokens? So the way you can calculate advantage is that the first step is to uh, calculate the scores for all the different tokens, which you can do now because you have the old log probabilities. And after that, you can have one single reward attached to the end, because the reward model is frozen. Remember, the reward model is not trained as a part of the PPO training. So now you have the score vector appended with a single reward value at the end. And then what you can do is you can pass all of this along with the values which you obtain from your value model, and you can generate these advantages and these returns also. Okay, so for all the tokens uh, which my trajectory has generated, I can now generate the advantages and I can now generate the returns. Remember that to generate the advantages, you would need the new log probabilities also. So you would have some, let's say, some version of your model which is already trained. So you use that version uh, to calculate the new log probabilities. And the old log probabilities anyways are calculated from the reference model. So at this step, I want you to have a very clear-cut understanding that before we even start the PPO training, I can have the advantage values calculated for all the tokens. I can have the values also calculated and the returns calculated for all the tokens. Now, once we do that step, there is another step which actually precedes these three steps. I should have mentioned that at the start. But what usually happens is that if you have a lot of trajectories, people don't process everything at once, but they construct mini batches. For example, in this, what we have done is we have 6 sequences, and we have constructed 3 mini batches. You can see here mini batch 1 out of 3. In the first mini batch, we have sequence 0 and 1. In the second mini batch, we have sequence 2 and 4, 5 and 6. And usually people in practice, okay, let me actually reset and okay, usually people in practice they do shuffling. So they shuffle between these sequences. You don't go 0 and 1 at a time, but you can do 0 and 3 first, then 1 and 5, then 2 and 5. And then you do the training for the first two sequences, and then you do the training for the next two sequences, and then you do the training for the next two sequences. Okay. So the version of the model which you are using to calculate the new log probabilities changes for each mini batch. Okay, so that is the version which you use to calculate the KL divergence. Now, after you sample the trajectories, you generate the mini batches, you calculate the generalized advantage estimations, you calculate the returns for all the single tokens in these sequences in the mini batches, you are ready to go with the next step. Now, what is the next step? The next step, in this case, I have mentioned it as a forward pass. So the order is a little bit jumbled up here. So here, this forward pass, the objective of this forward pass is to calculate the old log probabilities and the new log probabilities. So this new log probability is continuously being updated as so now we have started the training. Okay, so all the data which we have collected before that we have kept, but now we have started the training. And as we start the training, these old log probabilities, uh, these are fixed because this is the version of the model just before we start the training. But this new log probabilities are continuously changing as the number of iterations increase. For example, in the first iteration, it might have a different value. In the second iteration, it might have a different value, and so on. One thing I want you to understand is don't get confused between in the in the KL divergence also we have an old policy and a recent policy, but in the KL divergence, this old policy it refers to the reference policy actually, whereas this old refers to the most recent trained version of the model, and this new version is the one which is continuously being updated. So now, as you proceed through the forward pass, you do this for all the tokens, and you do it for multiple iterations. The values of the uh, new log probabilities will keep on changing. And once the forward pass is completed, you get to the main step of PPO, which is the loss calculation. Now, this is where I want to pause and I want to link it with the theory, the theoretical discussion that we have had. Okay, so first of all, we are looking at this sentence. Where is Pune? Pune is in India. So I'm looking at only the answer which is generated by the LLM. Now, what is this RT? Let's go back to the theory and understand it in a much better way. So, when we discussed about proximal policy optimization, we discussed about one parameter which we called as RT. So, this RT is the ratio between the new policy and the old policy. And this we have already calculated in the forward pass, right? Because in the forward pass, we are calculating the probability of choosing that action according to the new policy. Old policy we already know, which is the latest trained version of the model, but this is continuously changing as we are training our model. So this is the RT which exists here. Now, remember the advantages we have already calculated in the offline step. So we multiply this RT with the advantage, and then we get one value. But first of all, why we are multiplying the advantage with the RT? So let's look at the final formula. The final formula is this, right? Where we are doing a minimum of RT times advantage and clip times advantage. Okay. So first we need to find RT times advantage, which is this. And then we do clip of R times advantage, which is this. So this helps us to find the minimum of these values. And then we can construct the PPO loss using this. And then what we can do as a next step is this is actually exactly equal to the PPO loss. The next loss is the value function loss. Now, what is the value function loss? Which is the value predicted by the model minus the returns. Remember, we discussed that the returns are the target for the values, and these returns are already calculated in the offline mode. So we can calculate the loss by doing V minus R whole square. So we have the value loss here, we have the PPO loss here, and the entropy is just dependent on pi times log pi. So that we already know. We know the pi of the new policy. So we can calculate this PPO loss, value loss, and entropy loss for all of these different tokens. And here I have included multiple sequences. You can see one is Pune is in India, Mumbai is in India. There can be multiple sequences. And then you basically add all these losses and you get a total loss from that mini batch. And the objective for us is to then run a gradient descent to minimize this loss. So this is one example where I'm showing how these R values are calculated based on the old and the new values of of the probability predictions for all the sequences in the batch. And then okay, let's go ahead and understand what do we do after these losses are calculated. So after the loss are calculated, we just run this backward pass, and the backward pass is the first time where we update the weights of our model so as to minimize this loss. So in your mind, remember, okay, fine, there are many batches. First mini batch, we pass through, we train the mini batch, calculate the PPO loss, value loss, entropy loss, do a backward pass, update the weights, go to the next mini batch, then again go to the next mini batch. Similarly, we process a lot of mini batches in one single epoch, and like that, we can have multiple epochs during the training. Okay, so this is how I'll just play it from here, and then afterwards, you can just look at how the mini batches proceed. Now we don't do the initial part. The initial sampling is already done. Now all we do is we do these passes across the three mini batches. This is how our training becomes much more efficient because as the training proceeds, we are not calculating the advantages, we are not calculating the returns, we are not calculating the old log probabilities either. Okay, so all we are calculating is this new probability during the training. So it's not exact completely an offline algorithm, but it's online also because we need to calculate the probabilities to calculate the ratio, which is RT. In the RT ratio, if you look at this, uh, we have the ratio which is or the numerator is the probability according to the new policy, which we anyways have to calculate during our training run. The probability according to the old policy we already know, so we don't need to calculate that. Now, some of you might be wondering how many models are we running parallelly in the memory, right? So you can see here that the one model is the model which we are training, the LLM, our agent. The second model is this value model, which also we are training. The third model is the reward model, which we are not training but which is set in place. And the fourth model is the reference model, which is the output from the supervised fine tuning step. So in the memory, there are four different models which are used, and two models are frozen and two models are actively trained in the PPO step. So this is exactly now we have again going through the second epochs now. And in the second epoch, again, we are going through the three mini batches. So now you'll be able to appreciate these formulas. So you might be wondering, why is the R of t represented like this? You can see that. Let me actually explain this. If you do log of pi new minus log of pi old, it is log of pi new divided by pi old. And if you do an exponent of the log, you get the value which is inside the log, which is pi new divided by pi old. That is why people use this in practice. And the rest of the formulas now you will be able to appreciate much better after our theoretical discussion, which happened in the first 45 minutes to 1 hour of today's lecture. Okay, so why don't you run this on your laptop and understand all these steps? We'll take a break for 5 minutes and then we'll move to a very important section, which is the question of how do I implement this in practice, right? If you are implementing RLHF for a reference data set, you can't keep on doing this padding, masking, everything by yourself. Is there a framework which allows me to do this easily? So this will explain in the next phase. So first of all, what is this OpenRLHF? Let us have a look at it. So it's a very nice GitHub repo which has around 8K stars, and it is used by some of the leading companies in the world. If you look at the people who use it, companies like Google, ByteDance, Alibaba, Allen AI, all of these companies use it. And it's basically a framework which makes RLHF implementations very easy. They take care of all the things for us and make the coding process a lot more accessible and straightforward, especially for people who are not very well versed into coding all the aspects by themselves. So let's start to understand, and then we'll look at some practical examples also. So essentially, in any RLHF step, there are three steps which are required. The first step is the supervised fine tuning step, where you have a model which is pre-trained, and then you have a specific data set, and you want to fine tune the model on that specific data set. So that is where OpenRLHF can make that entire job easy for you. And then after supervised fine tuning, you train the reward model, and then you do the PPO training step, which we discussed in the lecture today. Now let's look at the supervised fine tuning step first. Okay, so this is the single script which you need to run for that purpose. So they have these scripts given under example scripts, and you can run this file, which is train sft llama.sh. Now there are some things to consider. First of all, let us understand what all these different parameters are. Okay, so some important things are here. Pre-train. This is the model llama 3 8 billion parameter model, which will be supervised fine-tuned. Okay, so this is the model, and you might be wondering which is the data set. So this is where you enter the data set. So you can actually look at this data set, OpenOrca. It's a famous data set which people use for supervised fine-tuning. So you have a question and you have a response, and then you fine-tune the model based on that. Now, apart from that, they have an input key and an output key. So here you can see input key is question, which is the input parameter, and output is the response, which is the target parameter of the supervised fine tuning. Okay, so these are the main, then this is the train batch size, which is, let's say if you have uh, 10,000 sequences to process. In one batch, you take 256 sequences. So you have around maybe 40 batches to process at a time. These are the maximum samples. If the data has too many sequences, you can ignore if it exceeds this value. Maximum epochs, this is the number of epochs, learning rate, all of these are standard. So, and then we use this module called deep speed. This is something which helps training large models and supervised in the supervised fine tuning step also. They have this section of applying chat template. What this means is that every model, right, it requires the data set to be trained in a specific format. And if you do this apply chat template, it usually means that it will pick the correct format for you. So it actually gives some examples for that. So for example, let's say uh, this is your data set. Okay, uh, this is what the user has asked. So the role is user. This is what the assistant has given. So the role is assistant, and this is uh, the next question which is asked by the user. So what you do is you pass this data set to this function called tokenizer.apply chat template. And depending on which LLM, from which LLM this tokenizer is created, it will actually format it in a proper way for you. Why this is required is that many LLMs are trained in a specific format where it is trained to answer questions. For example, any LLM is initially it is trained to just predict the next token, but many instruction fine-tuned models, they are trained to actually speak with humans in a very structured way. So this applying chat template is usually applicable when your downstream task is to use a model which responds to humans uh, in a way which typically humans respond to each other. Otherwise, it will just complete a sentence. It will not expect the format to be question and answer. So that is why we use this apply chat template. So if you look at this script, right? So which is the first script which all of you should try if you want to explore OpenRLHF. Train sft.llama. Here they have not used apply chat template because whatever input output pairs are there in the dataset, they are in the similar format to the ones which llama requires. So that's fine. That's not needed. But if you are using any other model like Mistral, etc., then you might have to activate this. And then I have implemented the same code quite recently last week, and uh, it costs some amount of money because I wanted the training to happen in a faster way. So what I did was I ran this script on the run pod with 8 GPUs in parallel, and the total cost I incurred was around $50 for doing this supervised fine tuning task, but it worked really well at the end. Okay, now this is the reference model which I keep on talking about when you calculate the KL divergence. That's why this is the first step in the reinforcement learning with human feedback process. Now, after this, the reward model training, which we looked at length, it has a very similar format. And here you usually use a model which is the supervised fine-tune model. And then so the same model which you did supervised fine tuning on, that model is used as the initial point for the reward model training. And other steps remain similar. This is the data set which people generally use for aligning model towards human preferences, or let's say if I ask a question to a small language model, what is the ideal method to hit someone on the head? Then it will answer that these are the ways to do that. But if you train the reward model based on this, then it will learn that, okay, fine, this is probably gets a bad score and it's rejected. So and it has huge data. You can see 5,55,000 rows. So this is used for this is the preference data set. Chosen key you need to specify, which is the chosen here, this one, and the rejected key is the rejected. So you have to specify that. If you have your custom data set, you can use that also in this. And then the rest of the things are very similar. You can see there is something called zero stage here, which is related to GPU processing if you have used data sets. So this deep speed is something which is generally required if you have large data sets. Okay, and then the last step is the PPO training step. So this is also something I tried last week and it worked. So for this you need to give two models. You need to give the reward model, and you need to give the supervised fine-tune model, which acts as the reference model. So remember I said there are four models which are required. So this is the reference model, this is the reward model, and the model that we are fine-tuning is fine-tuned from this reference model itself. And the value model is constructed from the reward model itself. So only two models are required, but in the memory there will be four models which will be working together. Okay, so now here you can see there are more parameters. For example, the first model is the reference model. So you need the number of 8 GPUs for that. Then reward model 8 GPUs, critique model 8 GPUs, and actor model 8 GPUs. In practice, 32 GPUs is very impractical. So I actually use this example from their scripts. They have an example which is train ppo llama.sh. Where is that? Yeah, this one, train PPO llama underscore ray.sh, and here they have used 8 GPUs. So this is also slightly on the higher side. Today I'm going to show some examples which you can simply run on Google Colab very easily if you do not have large data sets. But I want to give you this perspective because this is what people in companies and industries are currently doing for alignment tasks. If you really want to build something that is very relevant and that people can benefit from, then this is a very state of the art framework which has everything included for you. So it really takes away all the time to code all these different things. If you remember, for our previous example, to code our reward model, we had a long piece of code where we had the chosen answer, then the rejected answer, and the masks associated with these answers concatenated with the prompts, and then we use that to construct the reward. So all that is actually taken care of within OpenRLHF itself. Now what I have done is that I want to make this process of transitioning to OpenRLHF very easy for you. So I have constructed two very nice Google Colab notebooks which can run simply on a so this might require an A100 GPU for you to run, which is not very costly. And let me share this link with you. Okay, so let us go through the different elements of this code properly. Okay, so the first step here is to install OpenRLHF and install VLLM. If people are not aware, VLLM is a engine which is used for inference, and it makes inference very fast and very quick. So you have to run this and it will ask you to restart your session, so you need to run it again. And then what you do is the data set, which is the set of prompts I have collected from this data set. So you can have a look at this. Is also very popular data set. Remember I said that for PPO training you need a bunch of prompts. So you can use this data set for constructing those set of prompts. And then I divided it into training 116 sequences and testing 160 sequences, and you get this distribution. And we can actually look at some prompts. So here is one prompt: answer the question given this paragraph. Paleontology. This is a long question. So okay, so there are a bunch of questions which you can actually look at. These are a very carefully constructed set of prompts. You can see the number of uh, Downloads also might be, yeah, last month 500 downloads. So this is by OpenRLHF itself. Okay, then as I said, the PPO training requires these four models. We need the reward model, which is trained after obtaining the SFT model. Actor model is initialized from the SFT model. The critic model, which is also the value model, that is initialized from the reward model, and the reference model is initialized from the SFT model. So we are going to use this small LM2 135 million instruct model, and we are going to use this reward model, which was again created using OpenRLHF itself. So now these are just some code you need to run installation of Flash attention package. But before that, I hope you understand why we are using these supervised fine-tune and the reward models. The supervised fine-tune model is the base point from which we are going to train our model from. That also serves as a reference model. So we don't want our model to deviate too much from this SFT model, which comes in two places actually, one in the KL divergence and one in the PPO step with the RT of theta and the clip function, which we have towards the end. Now, we can actually check the supervised fine-tuned model performance using the reward model. So initially, we don't do any kind of PPO, but just want to check how the supervised fine-tuned model performs using the reward model. So there is a distribution. Yeah. So this is how it performs, which is fairly. There are some negative rewards and some positive rewards also. So our hope using PPO is that this curve will either for higher rewards the frequency will increase, or this is slightly shifted towards the right. So even if one of the two is satisfied, we'll say that we have been successful. So that is our objective that we want to proceed with. Now we actually train this using OpenRLHF, and we are using a framework called Ray for this. Ray is a framework which is actually used for running jobs like this, where we have four different LLMs. And here within one single collab, actually, you can learn how to use Ray. So here, GPUs one, there is only one single GPU, and this code works fine. And here you can see there is something called micro rollout batch size. So rollout batch size means that these there are 8 trajectories which are processed at once in a batch. So remember in our visualization we had a batch size of 2. I think we saw 2 sequences processed parallelly. So these are 8 sequences processed parallelly. So in the RL literature, you might say people talking about rollouts a lot. So rollout simply means that in one single batch, how many sequences you are processing parallelly. So these are 8 and 8. And then zero stage is 0 because we have one single GPU. We do not have multiple GPUs. And this is the supervised fine-tuned model. This is the reward model. And rest of the things are related to VLLMs. We are using an apply chat template here. Okay, and now once you do the training, you will see the training proceed in a way. This is given by the Ray engine, where you see all these different models working parallelly. It will take around 1 to 1.5 hours to run for this entire run. Not a very long time, and then we can actually compare the supervised fine tuning and the RL train and the RLHF model. So this is what I got. So you can see there are performance improvements for sure. These outliers with very bad rewards are first of all prevented. You don't get any blue line here. Then if you look at the frequency of higher rewards, they also seem to be here. The frequency of higher rewards, they are higher. For example, if you look at some of these orange lines, they have significantly higher rewards compared to the blue lines. And if I could run this training for more, I think I would see more differences. So these are quantitatively the average reward has moved up from 0.099, it has moved up to 0.1366, which is quite good, which means that my RLHF training has actually worked fine. So if you run this for more epochs, you will see more prominent differences in this training step. But now, when you go back and when you look at the code, you will see that you will be able to easily understand different aspects of this code, because many things are actually abstracted using the Open RLHF library. So you don't need to really understand how to do masking, padding, all these nitty-gritties. But once you run this, you will get confidence of, if you have your own data set, if you have your own problem statement, you can simply use a similar analysis and you can train a model using RLHF and you can get decent results out of it. One of the challenges with RLHF, of course, is the out of memory error, because there are four models loaded in parallel in the memory. But if you are working with larger models which have billion parameters in size, then you cannot run those codes on Google Colab, and you need to spend some money if you want to go in that direction. Okay, so there is another Google Colab notebook here, which actually shows how the reward model was trained using OpenRLHF. So let me share that as well. Okay, so to train the reward model using OpenRLHF, the first step remains quite similar, which is loading the packages. And then this is the model which we are going to train the reward model on. So you need to start with some model, and we start with this instruct, which is the supervised fine-tuned model. And then now this model structure also you can actually begin to understand. Uh, let's see. So this is the model, this is the vocabulary size. 576 is the hidden dimensions. And you can see this is the final projection layer. So far we have not looked at the reward model, but when you look at the reward model, this will be 1. This will not be 49152. And again, we look at this data set for the preference training, and we split the data set and into 400 training, 16 evaluation, and then when you proceed with the training, again it looks in a similar format, where you give the initial model that you want to train the reward model on, and you give the data set, evaluation data set, chosen key, rejected key, apply chat template, train batch size, micro train batch size, learning rate, API key, for this is for WarnDB logging, and then this actually proceeds properly and you get a reward. And now, yeah, so this is what I wanted to show you. If you look at the reward model, you can see here the output is single, right? Rest of the things remain the same. And this is exactly the same that we are discussing in today's lecture through some schematics and diagrams, that the output of the reward model is one single scalar. Okay, so now we can, here I have just tested some examples where with the rejected text you get a bad reward, and chosen text you get a good reward, so which means the model works fine. And then I have plotted some histogram for the chosen sequences and the rejected sequences. The objective was to see if there is any clear division. I actually wanted all the blue lines to be on the right and on the which is true, kind of everything has a positive reward. But I'm curious why nothing is coming on the negative side that much. So overall, it seems to be working. The chosen sequences are getting more rewards than the rejected sequences. So yeah, this is how you can simply train a reward model using the OpenRLHF framework, and then you can proceed to do PPO. So first, I want you to be comfortable with these two notebooks, understand each and every single aspect of it, and then uh, take higher models, take bigger models, and then run it using parallel GPUs.